Voilà.
Et du coup, c'est le programme que oui.
Bonjour. Bonjour. Un, deux. Et bonjour. Et ah. Et
give a short motivation, including a reminder about what ontologies are. Then I will introduce the method, as well as some ongoing work on a tool that can be used in the workflow of the method. And I will end with a brief conclusion. So ontologies have been suggested as a technology to make data fair. For this audience, and considering the previous talks in this workshop, I do not need to explain FAIR anymore. So what were ontologies? Well, ontologies can be seen as a way to define the terminology in a domain by defining concepts, relations, and axioms. And here is an example of an ontology that we developed. There are some concepts related to.
Ça sera le premier. Ok.
Hey, my name is Patrick Lambrix, and I work at
I can speak. Can I see myself also? Big echo. Echo, echo, echo. Good morning, everyone. It's my pleasure to introduce the session on ontologies. And I'm happy to say on this last day of the workshop that we have quite a bit of experience. We have more than 50 years of experience in ontologies here in this session. We have 3 important speakers in this field, but of these 50 years, you have to also relate that I contribute only 2% of this experience. I'm Thomas Palstra. I'm a solid-state chemist, and my efforts have been in synthesizing, characterizing, and establishing properties of materials and devices for mostly electronic properties. I have no experience in ontologies, but over the work of working within the FAIR system, it has become apparent that ontologies are an important ingredient to also have a good conceptual agreement on this in material science. Thus far, we have heard various definitions of ontologies, and they were mostly related to different electronic structure calculations. I hope that we can broaden this field significantly and that we can say a bit more about the general use of ontologies in a much broader sense. For me, ontologies relate to a design, categorization of materials in a structure that could be hierarchical or network that identifies certain materials with particular attributes to within this set. But we are happy that Professor Lambrechts and Guisardi will provide a proper definition of ontology, and they will also give the relevance of interoperability within the FAIR system for ontologies. In my language, interoperability is not just about different codes that interact with each other and means that electronic structures can be related and interacting with each other. But for me, ontologies means that you can also relate this directly to other properties, such as, for instance, transition electron microscopy, which gives direct information about electron densities, and also, for instance, with X-ray diffraction, which is basically only the Fourier transform of the electron density. So let me give you my personal examples of ontologies. And for me, it's something that I've worked on for quite a long time. And for me, ontologies as a solid-state chemist of small inorganic compounds are more related to symmetries. And let me give a few examples during my career. So when I started, I had my first position at AT&T Bell Labs about 30 years ago. And at that point, the boss of my department head, Bob Lodis, who was a solid-state chemist, came to me and asked me, Tom, I have a new magnetic material. Could it be of interest for magnetic storage? And I knew immediately from the space group that I do not know all by heart, but I knew sufficiently of space groups that this was a cubic material and therefore of no relevance for magnetic storage because there is no anisotropy involved in these cubic materials. But what are you going to say to the boss that just hired you a week ago? So I told him, I will get back to you. Let me think about it. And 2 days later, I told him I did not think it was a good idea. 1 year later, he came back to my office and told me, Tom, you told me that it was of no interest. I didn't believe you, so I had it checked out at the university. And luckily for you, it turned out to be true. So symmetry is a way of characterizing materials that have vast consequences. The second example, some 20 years ago, I was researching materials related to the perovskites. And it's a well-known perovskite-related compound yttrium manganite, which is actually not a perovskite, but an hexagonal material, more towards the big-spite structure. This was related, of course, to the interest in the perovskites in those days of high TC materials, as well as with the colossal magnetoresistance materials. It turned out that from the 1950s, this material had been characterized in the wrong space group. And everyone in the literature thought that manganese 3+ was off-centered in the structure. And with the techniques that we had at hand in those days, it was quite easy to see that this was untrue. And of course, you have to go to a barrier to convince others that this is indeed the case. And indeed, it was the yttrium that is off-centered and not the manganese. And this led to a completely new way of looking at this material. And this was one of the first types of multiferroics, a compound which is both magnetic and also ferroelectric. So it lacks inversion symmetry, and it also lacks time reversal symmetry. And more recently, 10 years ago, we started to get interested in a polar ferromagnet, a material that lacks inversion symmetry and also lacks time reversal symmetry. This is in principle impossible, because a ferromagnet, well, 99% of the ferromagnets are metals, but aside from that, a ferromagnet defines itself to be as a material which has also inversion symmetry. And the absence of inversion symmetry means that something else is going on in this material. And this spawns the field of topological excitations, in this case called skyrmions, where you have all kinds of topological excitations in your material, giving rise to new materials opportunities in terms of storage and in terms of properties of these materials. So now we are witnessing an enormous amount of new materials, novel databases. And we need to define which properties are desirable in order to classify the interest in these materials. So besides electron structure, I think we should also not only include symmetry, which is already included in it, but also response functions, chi of k and omega, but also transport. And somehow I think we should also include interfaces, because the interface is the most relevant part to become relevant in device physics for actual functioning of materials. So in recent years, the ontologies have been not so successful, in my opinion, yet in inorganic solid-state chemistry, but mostly successful in biochemical systems. And I'm also happy then that Karsten Baldauf will introduce this into this topic and will give his own personal experience here. The first talk, though, will be given by Patrick Lambrix. Start my notes. Patrick is at the University of Linköping, and he is a computer scientist. In his PhD thesis, which was called The Part-Whole Reasoning in Description Logics, in 1996, he introduced representation and reasoning about the part of relation. So an example is a finger is a part of a hand, and to use that to define description logics. Description logics are formal languages focused on representations of concepts and relations with a focus on reasoning using there is a relation. So for instance, a dog is an animal. Description logics are the basics of OWL, OWL, the current much used language for representing ontologies. Patrick has worked with ontologies for about 20 years. He started working on ontologies in the field of life science, in particular, to provide a way to integrate information from different databases with biomedical information. And although the name FAIR was not coined yet, this essentially dealt with the eye of interoperability in FAIR. And since then, his group has developed tools that help ontology developers in different ways. So he developed systems for aligning, debugging, and removing and completing ontologies. Aligning means connecting different ontologies. Debugging means the finding and removing of wrong information. And completing means finding and adding missing information. And he also has developed ontologies in animal health surveillance, security, material science, and sports. And this talk will essentially introduce the method based on text mining that proposes concepts that should be added to an ontology to make the ontology more complete. And to give a little bit in these daring times of COVID, Patrick has also a local issue. His neighbors are in the process of moving and refurbishing the house. So he has his talk pre-recorded, but of course afterwards he will be happy to answer questions. So let me ask Gianmarco to start the presentation.
Hey, my name is Patrick Lambrechts and I work at Linköping University and part-time at the University of Gävle, both in Sweden. In this talk, I will introduce a method for extending ontologies. First, I will give a short motivation, including a reminder about what ontologies are. Then I will introduce the method, as well as some ongoing work on a tool that can be used in the workflow of the method. And I will end with a brief conclusion. So ontologies have been suggested as a technology to make data fair. For this audience, and considering the previous talks in this workshop, I do not need to explain FAIR anymore. So what were ontologies? Well, ontologies can be seen as a way to define the terminology in a domain by defining concepts, relations, and axioms. And here is an example of an ontology that we developed and that aims to represent essential terminology regarding materials design. There are some core concepts in red, such as calculation, property, structure. There are some concepts related to computation, such as different computational methods. Some concepts related to structure, and then some related to provenance. Further, there can be relationships between concepts. So for instance, there is a relation has output structure between a calculation and a structure. There are also axioms, in this case to represent is a relation, where we have a hierarchy of different computational methods. So the way that we use this ontology is in an ongoing project where we aim to provide semantic and integrated access to materials databases. We currently work on the databases in the Optimate consortium, where the idea is that by using the ontology and by creating mappings between the schemata of the databases and the ontology, we will allow querying over multiple databases and will allow queries to take into account relations in the ontologies. In the paper mentioned at the bottom, there are some examples of queries that could not be asked using the current interfaces of the databases, but which you can ask and you would get results using the ontology because the information is actually in these databases. So to be able to provide good services, it's needed that these ontologies are of good quality. And I will focus on one particular quality aspect, namely completeness. So the idea of completeness is that we want an as high coverage as possible of the necessary concepts, relations, and axioms. In general, it's not very easy to say when an ontology is complete, but it is actually possible to define when a version of ontology is more complete than another version. And incompleteness can be missing concepts, missing relations, and missing axioms. Now, these missing concepts, relations, and axioms are problematic in semantically enabled applications, such as ontology-based querying. And here is an example for the influence of missing axiom. So we're querying PubMed here. PubMed is a database with over 30 million abstracts of research articles in the biomedical field. And we're going to query using scleral diseases. So we want the documents that are about scleral diseases. And in this case, PubMed will use MESH, which is a vocabulary, and it will take into account that scleritis is a scleral disease. So in that case, the system returns us 1,663 articles according to a query that I did some time ago. Now, what happens if this relation between scleritis and scleral diseases would be missing? Well, then the result would only be 948 articles, which means that a large part of the articles that are interesting for us are actually missed. So in the remainder of this talk, I will introduce a method to find new concepts and axioms to be able to make an ontology more complete. Our proposed method has two parts. In the first part, we use unstructured text, for instance, research articles, as an input. And as an output, we receive a list of frequent phrases, as well as topics which a domain expert then needs to validate. In the second part, we try to find additional axioms using formal concept analysis. So let's look a bit closer at these two parts. So for the first part, we use an existing system called the TopMine system. It's a data-driven system. It does not need any background knowledge nor linguistic rules. It works on phrases rather than on words, and it has two steps. In the first step, contiguous phrases are collected and counted, and phrases that occur at least as often as a given threshold are considered frequent phrases. In the second step, topics are generated, and essentially, topics can be seen as a probability distribution over words or phrases. So let's look at an example. This is an example from a biomedical text. Given a collection of documents, the topic model approach assumes that each document has a distribution of several topics, and each topic has a distribution of a number of words or phrases. For example, in this document where we look at topics based on words, the approach returns 4 topics. Each topic has several representative words with a confidence value to state how likely this word can represent this topic. So in the first topic, we have, for instance, gene, DNA, and genetic. TopMine will then represent the topic as a collection of phrases rather than words, as in this example. In our second step, the formal concept analysis phase, we use a topic phrase table. For instance, in this table, we can see that topic 2 is represented by phrases 2 and 3, and topic 3 is represented by phrases 1, 2, and 3. And comparing these sets of phrases allows us to conclude that, and thus we could suggest a hierarchical relation between these two topics. Domain expert will then need to validate this. In the remainder of the talk, I will not get back to this stage because in the 2 experiments that we did, In the first experiment, we didn't find new knowledge that was not found in the first step. And for the second experiment, we actually didn't reach this phase yet. So in general, the domain expert is involved in validating phrases, topics, and axioms, and needs to decide whether concepts or axioms should be added to the ontology. Now, for our own research purposes, we introduced different validation categories, representing whether knowledge should be added to the ontology, this is the add label, or we should add this knowledge with a small modification, that is this -m, or whether the knowledge already existed in the ontology, the exist labels, or whether it is not relevant at all, this is a no label, or it would be a concept which is too general for this ontology, is a no G label, or if it's too specific, and then we have labeled it with a Q. So let's look at two experiments. In the first experiment, we tried to extend two ontologies in the nanoparticle domain. These are nanoparticle ontology with 1904 concepts and 81 relations, and eNanoMapper ontology with over 12,000 concepts and 4 relations. So we collected 627 abstracts from the nanoparticle information library. We experiment with different settings for top mine. The first number in the table tells us how many topics we want. This is a setting you have to provide beforehand, and we experimented with 20, 30, and 40. The low and high refers to how easy or difficult it is for words and phrases to be merged in longer phrases. So for the phrases generation step, we found, for instance, that amorphous silicon should be added to the ontology, and gold nanoparticle already existed in the ontology. The best result for the nanoparticle ontology suggests that there should be 32 concepts added with the same name, and 4 additional ones with a slight modification of the phrase name. So 36 in total. It also found over 40 concepts that were already in the ontology. And existing concepts give us some kind of a sanity check that this method actually does find relevant stuff. For eNanoMapper, we found 32 new concepts. Similarly, in the topics validation step, it was suggested that mesoporous silicon nanosphere should be added, and we already had chemical vapor deposition in the ontology. So for both the nanoparticle ontology and for eNanoMapper, we found 10 concepts that could be added, but actually only 2 of those were not found in the previous step. So there are actually ontology learning methods and systems, and these could be used for extending ontologies. And because if you can learn the ontology from scratch, you could also, in principle, use it for the extending the ontologies. So we wanted to compare our result with some ontology learning systems. We compared it to Text2Onto. It was actually the only system that we could download, but it is actually a well-known and very popular system. For extracting concepts from textual resources, it uses 4 algorithms. And as it returns lots of validation candidates, it's also word-based, we check the first 100, 200, 300, and 400 suggestions. And in this table, we show some results when we use all 4 algorithms. So in the precision part, we see that our system has a higher precision, which means that the percentage of the suggestions that are relevant is higher than for text to onto with up to 400 suggestions. But we also see that we have maybe similar amounts of new concepts that can be added. So what is the relationship between these sets of concepts? Well, here are just a few examples. And we know that some concepts, marked in blue here, are found by both methods. The blue ones, the green ones are only found by our method, and red ones are only found by text to onto. So it actually seemed that these approaches are complementary to each other. So now the question is this extending ontology actually worth the effort? Well, we spent about 10 hours per person for 3 experts. 2 of them were ontology engineering experts, and 1 was a materials science expert. For the nanoparticle ontology, we found 35 new concepts. We added 42 new axioms representing isorelations between sub and super concepts. And these new axioms actually led to changes in the sub and super concept sets of 72 already existing concepts in ontology. So that means that for 107 concepts, the results for queries using those concepts will become better. For eNoMapper ontology, we introduced 32 new concepts, 37 new axioms representing isorelations between sub and super concepts. And this led to changes for 32 already existing concepts. And thus, for 69 concepts, the results for the queries will be better. We also note that if the concepts are used as domain and range restrictions for relations, there will be even more influence. So in the second experiment, we want to extend MBDO. It is still ongoing work, but the idea here was, can we actually use the ontology as a seed? So MDO is the ontology that I described earlier. And the idea now is to use the 32 concepts from MDO as a seed for our system. So we use these 37 concepts as search phrases to 2 databases connected to journals. And when we did that, we received over 8,000 different documents, where we only collected the title and the abstract. The reason for this is that we think that the main phrases and the main concepts in the field will appear in this part of the text. We did some pre-processing, such as only using lowercase, removing punctuations, removing words of length 1 or 2. And after this pre-processing, we had over 21,000 distinct words occurring together over 800,000 times. Many of these words appeared only less than 10 times, 72%, while these 17 words, which are very general, they occurred more than 3,000 times. Then we also used some stemming to remove redundant phrases and also to reduce the work of the domain expert. So all these phrases would be represented by one phrase, which is this one. And in addition to a minimal threshold for deciding whether a phrase is frequent, in this experiment, we also added a maximal threshold to remove phrases that may be too general. So for instance, it would allow us to remove these very general words by setting a maximum threshold of less than 3,000. So in this figure, we use as the base case a minimal threshold of 10. So phrases need to appear at least 10 times to be a frequent phrase. And the maximum threshold of 8,000, which actually no phrase reached. So essentially it means there is no maximum threshold. When we compare to other settings, we can, for instance, change the minimum threshold to 15, 20, 25, and 30. And when we do this, it becomes more and more difficult for a phrase to be called a frequent phrase. And thus, more and more phrases will actually be removed. Similarly, when we reduce the maximum threshold, more and more of these general phrases will be removed from the suggestions. Some phrases are also added, and this has to do with the feature in TopMine, which uses a quality threshold, and sometimes subphrases will attain this quality threshold when their superphrases are removed. We are still working on the evaluation phase, but here's an example of the results. For a minimal threshold equal to 30 and the maximum threshold equal to 500, the system suggests 131 frequent phrases, of which we may get 88 candidate concepts. So some phrases may lead to multiple concepts. Whether all of these 88 concepts will make it into MDO, this still remains to be seen. Now, it is of course possible that topics overlap with their phrases. And here are some results from 2 different settings. We see that the more topics there are, the lower the overlap will become. And the more overlap you have between topics may actually indicate that maybe there's a relationship between the different topics. And this may lead to new relations or axioms in the ontology. So in the first example, it's very likely that there is a relationship between topic 1 and topic 6. So based on the 2 experiments, we can make some general remarks. Our method is based on phrases rather than words, as we assume that other methods can easily find words that could lead to concepts in ontologies. So our method could be seen as complementary to those approaches. We also noted that a higher mining threshold for topics gives fewer phrases in a topic, and usually fewer phrases in a topic makes it that the results are easier to interpret for the domain expert. Now, something that is quite difficult is to decide on what should be included in the ontology. We need some more information, or we need to decide on the scope of the ontology beforehand. And this may be influenced on the application that we still have in mind. So for MDO, this is exactly the stage where we are now. The application that we envisioned is mainly, or at the moment, is semantic and integrated access to Optimate. So this will influence what kind of concepts will make it into the ontology and which not. And further, it was clear that tool support is needed for the validation phase. In the first experiment, the domain expert validated the information in Excel files and also noted down which concepts and axioms should be included in ontology in these Excel files. And this is, of course, not the ideal way to do it. So in the remainder of the talk, I will show some slides regarding a tool for validation of phrases, which we're currently developing. At the moment, we've only looked at the phrases step. The topics step is future work. So the tool follows the workflow of the validation. First, it deals with the phrases. And then there's a step for going from phrases to concepts. Then you can add some concepts which are actually not related to phrases. And then finally, there is support for adding axioms as well. So for instance, in the phrases step, you can upload the ontology that you want to extend, as well as lists of frequent phrases. And these lists of frequent phrases can be generated by TopMine, as in our approach, or it could be generated by any other system. One of the things that you can do in this phase is, for instance, checking whether there are already concepts related to this phrase in the ontology that you want to extend. So here we have the list of phrases. And we're working on the phrase Hartwig-Fock. And we see Hartwig-Fock method is already in our ontology. In the next step, you can define new concepts based on the phrases, or by using the phrase as is, or by making some small changes. So for instance, here we have for using the phrase as it is, and here we have for defining a new form of the phrase. And here it shows which phrase we're dealing with. Then there is also a step that allows you to add new concepts which are not related to phrases. And this was a request by the domain expert, where he found that he needed to add additional concepts inspired by what he was validating at that time. In the last step, we add axioms. So in this example, we are working with the concept electronic band structure type. It will appear in this in the pane. You can then select concepts from the ontology that you are extended, and you can then say, for instance, that an electronic band structure type is a property. And then it will appear in the system. The system will also tell you about some consequences of the decisions you make, for instance, cycles. So in this example, there is already information ontology that crystal lattice type is a Bravais lattice type. And now the domain expert wants to add that Bravais lattice type is a crystal lattice type. The system will then note that this would lead to the fact that these concepts are actually equivalent. And then let the domain expert decide whether to proceed or not. The system also has some other functionality. It is possible to search in phrases, concepts, and axioms. During the whole process, it's possible to take notes in the system. You can also mark phrases as finished processing so that you don't have to remember what you've finished. There is also some simple ontology visualization that shows both the original ontology as well as the added new concepts and axioms. And you can save your results in OWL and Excel. So as a conclusion, we proposed a method for extending ontologies with new concepts and axioms. The method is phrase-based and it's complementary to the word-based approaches. And I do think that extending ontologies to make them more complete is worth the effort, as it raises the quality of the ontologies and therefore the quality of the services that use these ontologies in semantically enabled applications. So let me finish by thanking some of my colleagues. Rika Tamiento is our domain expert, my colleague, and Guanyu Li, Mina Apnikuripur, and Ying Li are our students. And we also thank the Swedish Research Council, the Swedish eScience Research Center, Swedish Agency for Economic and Regional Growth, and the National Graduate School in Computer Science for their financial support. Thank you for listening, and if there are any questions, I'm happy to take them.
Thank you, Patrick, for this very impressive overview or efforts that you are taking. I'm looking for questions from here as well as from the chat. Let me start myself, and then I can look at the chat who is willing. But for me, one of the questions is, how do you think the relevance of this? Because it appears that the relevance is mostly or emphasized as for the people that analyze the text that are out in the literature. So to what extent should this be also common knowledge for the people that write the research manuscripts?
I think for building the ontologies, the researchers don't really need to know that much about the ontology. Of course, if we think a step further, once you are aware of this, you can actually write in a way so that when people are going to use the ontologies to find your research articles, your article will be found in a much easier way. Another possibility is that the people who publish the articles, they would maybe do some automatic matching between concepts in the articles and concepts in ontologies that they use for their search systems. And in that way, for the actual search for articles, this would be beneficial.
Thanks. I see that Matthias Scheffler has levé la main. Matthias.
Yeah, it goes a little bit in this same direction. Somehow, Patrick, the way you describe it sounds that building an ontology is somewhat very subjective. I mean, it's built by experts who define some relationships, but of course, if you look at standard things and if you do text mining, then I understand actually that you may be helping a lot. But if you look for new scientific properties or basic research, I also see some danger in that, because I mean, you build this, or the so-called experts build some relationships, and then I guess it's more meant that the non-experts can use that, right?
I think as well, the experts also should use it. I see ontologies as a living thing. Gene ontology, which started 15, 20 years ago, is still a living thing. Concepts are becoming obsolete. New concepts are being added. I think the ontologies should grow together with the field, actually.
Okay, so ontologies really, in that sense, and starting with your very first thing is that quality is actually completeness is some quality mark. I mean, in principle, I would say then ontology is never complete, but actually you approach it better or better, right?
Right. Essentially, that's the case. That's why we're saying also that it's not easy to figure out when an ontology is complete, but you can actually define completeness, a relationship of this version is more complete than another version.
Yeah, I think actually more than the other, I agree, but being complete is really a limit which I wouldn't see that you can even achieve that.
Mm. Yes, I think so.
Also, two related questions that have come out in the chat from Rafael Ritz, who asked, what do you do if the experts disagree? Or there is a second remark, other ways to express something like precision, or how sure are we about certain parts?
Yes, so experts definitely can disagree. As a computer scientist, what I would do then is trying to find a way to make them agree, or what we sometimes do is having some kind of majority votes. That is the easy way. Another way could be in other fields, there are sometimes different theories about the same thing. And then sometimes you have to create different ontologies based on the different interpretations, different theories.
And yesterday there was quite a bit of attention also on precision, accuracy of your data. Can that be included somehow?
I'm not sure what the actual question is.
There is a question from, I cannot read who.
So which kind of precision? That's what I'm wondering.
It's the same person, Raphael Ritz. He mentioned, are you considering ways to express something like precision? Or how sure are we?
Okay, yes. Yeah, so there things are still in infancy, I would say. Some people are starting with probabilistic ontologies, where the idea is where you can actually express these kind of, well, if you want to say accuracy or how much you believe in that this is actually true. But not so much has been done yet in that field.
Okay.
It's definitely interesting.
And then a last question from the chat. If the moderator can move it back into view. Could you move up? Well, there are many more questions in the chat now. Okay, can you move it up?
Okay. Yeah. YouTube is even worse.
How easily, that's Matthew Evans, who asked, how easily can ontology extension be decentralized or distributed? Would this effort be easier or harder if every materials database had already created its own ontology?
Yes, essentially every materials database has created its own schema, and maybe they would call that an ontology. But I would rather have that databases in the same domain share an ontology so that they create this together. Then, of course, there will be overlap between different databases in similar domains. So I don't believe that you can have just one ontology, but what you need is a set of ontologies with mappings between them. And yes, therefore in fields that are close to each other, I think you want to decentralize and distribute that. A good example is Open Biomedical Ontologies, which is a website with over 50 ontologies, the biomedical field. And one of the things that they want there is that you have a very good scope for your ontology, but you have to work together with other ontologies to define the overlap. I think that's a very good way to go.
I think I will leave the remainder for the discussion at the end of the session. And I would like to thank Patrick again for his beautiful presentation. Thank you, Patrick.
Thank you.
That's what we need. And then we go to the second talk, which is going to be presented by Karsten Baldauf. Karsten is a scientist at the Fritz Haber Institute in part of the Max Planck Gesellschaft in Berlin. And also he is a representative of the board of directors at the Institute. He has received his PhD in biochemistry from Leipzig University and then spent time in Dresden and in the Institute for Computational Biology in Shanghai. His interest in machine learning and ontologies stem from the fact of being confronted with large amounts of data that we can create nowadays and believe that we can use it to extract more than a single number. Karsten will discuss aspects beyond the usage of ontologies to characterize stored data, and in particular, how agents can move through a world that we define by the ontologies and address how to extract useful information. Karsten, floor is yours.
Thank you very much. Is the microphone working? Yes. Excellent. First of all, it's a little bit a humbling experience. It's closer, better. Okay. It's a little bit humbling experience as the speaker before me is an expert in the field and the speaker that follows me is also an expert in the field, and I'm obviously not, right? So I have an interest in this. We started at this at some point, and we are essentially stumbling our way through using ontologies in material science. The work that I'm presenting is mainly based on the work by Maya Olivia Lenz-Zimmer. She's a PhD student. She's about to finish her PhD very soon. And she did an excellent job in our first path towards semantification of material science. When I wrote the abstract and decided for the title, I did not yet know fully which session I will be in. And also during the talk, essentially, or preparing the talk, some things became a bit clearer to me what I wanted to talk about. So essentially, I would rename my talk a bit into how I try to understand what ontologies are in the end actually good for. Yeah, because I think this is really something that is complicated for the field at the moment. We see this promise of using ontologies, but we do not yet really know when and how we will be able to use them. Because I think on the way to actually getting something out of it, we still have to develop a lot of things, add more data, understand more how we use and also develop ontologies. Yeah. So in that sense, I like Patrick's talk a lot. I mean, this tool that he presented on how we can essentially create ontologies might be a very useful thing. So where we start. So I'm from Berlin. I'm related to Matthias' group. So obviously we start from Nomad, right? You know this by now already, but I still would like to give a little. It's annoying. Unfortunately, I can't really point in the Zoom share, but you see at the left-hand side of the thing, you see computers. People compute. They do simulations. They upload the simulations then partly into the Nomad repository where the raw data is stored. Yeah, that's a nice thing. We have all the raw data. We can make all the raw data of these 40 different computer codes available. The magic happens then when the data gets normalized. So this Nomad meta info, Patrick also commented on that already a bit, is already some sort of an ontology, maybe a bit low level, but there is already structure in the data. And we are going to use that also in the following slides. And then even more magic can happen. So we see in this Materials Encyclopedia ways to analyze data. Yeah, and this is also an aspect that I'm going to use, or that Maya has been using in her talk, in her work, and that I will be presenting here in my talk. Okay, just quickly on the Nomad meta info. So the Nomad meta info is essentially the basis for our ontology development here, contains quantities. That means labels for the actual data values. You see here, for example, on the right-hand side, a schematic representation of this. So everything that is red is essentially data, and everything that is black, left of the red one, are essentially the labels for these data values. No? The whole thing is structured by means of sections in order to also make it, in the end, human readable mainly. There are categories that essentially represent first basic semantics, so relations between concepts. And there are other things like units that we need in order to describe physical quantities, and also references to structure the thing, so that, for example, a total energy has meaning only if there is also information about the system or the method that it was computed with, or for. However, the Nomad meta info itself represents not yet an ontology. So there are many DFT people around. So we always need to have a ladder when it comes to accuracy. So there's also a ladder here for these knowledge organization systems. So the simplest version would be, so would be a list of words, or simple glossaries and thesaurus concepts that are not yet helpful for this semantic approach. So the more we go up and to the right, the stronger this semantic concept, this connection between different quantities get. And with this, we get towards a level of understanding, and to a level of a computer being able to understand the concepts that we formulate. Yeah, this is the goal in the end, or one of the goals, I would say. So an ontology definitions are, I've read several, and they all are a bit, complicated. An ontology is formal. It's a formal, explicit specification of a shared conceptualization. Yeah, so the formal points already to the fact that it's supposed to be machine readable. The explicit specifications mean that the concept, properties, relations, functions, constraints, axioms, and so on are explicitly defined. Yeah, it really must be written down. It's shared, so that means that it has to come out of certain community consensus. No? That is not new. I mean, that's what people do at conferences. They talk about things, and at some point they agree on a concept. Yeah. Here, the next step would be that it has to be written down. So in an ontological way. So with that way, we get an abstract model, or typically it's always, of course, also a simplified view of phenomena that happen in the world. In our case, that make up materials and their properties in there. That's the way we went also with the Nomad meta info to develop an ontology. You see on the left-hand side, you see exactly again the metadata scheme of the Nomad meta info. On the right-hand side, you see this as a top view on the ontology. So that's the top layer of the Nomad meta info ontology. I will not go into much detail, but you see the representations between, you see the links between the concepts. You see, for example, things that like has variable dimension. That means that we have that we can define the dimensionality of properties and so on. So with this, we can represent the data in the Nomad repository in an ontological way. What this is now good for, so we start on the left-hand side again, right? You see, we have a data set that can be, for example, the whole Nomad archive. And in this data set, we have individual entries. In our world, these are typically single point electronic energy, electronic structure calculated. So at DFT run, yeah. If we now use the Nomad meta info ontology on that, we can populate something called a knowledge graph. So while the ontology itself is kind of empty, right? It's a catalog. Like we have here books in. No, I have. Yeah, you see the books. Yeah, we have books. They are catalogized. They are cataloged, and the information is in the books, but not in the catalog, right? Okay, we can create such knowledge graphs. Then, as I said, the knowledge graph in the end is kind of the ontology decorated with the actual data, at least in the way I start to understand this. Yeah, so we see here a kind of simple example, like we have the University Catholique Louvain, which is in Louvain, which is in Belgium, and which is also a university, a higher education institution, and it grants PhDs, bachelors, masters. Yeah. With this, we can, for example, also infer certain new knowledge, for example, that we can do a PhD in Belgium. Yeah, I mean, it's a simple example, but that's, again, how I understand, and maybe people can correct me there, the way I see the difference between a knowledge graph and an ontology. The knowledge graph really is then the knowledge represented in the way the ontology gives us the structure. The good thing about such knowledge graphs is that they are databases, so they can be queried, that they are graphs, so we can analyze their network structure, so connectivities between edges, and they are knowledge-based, so they, we can use formal semantics, and we can interpret the content of such a knowledge graph in order to infer new facts, like the very clever PhD example here. So, but what we want to do in the end is we want to use such technology in order to answer material science questions, right? So, and there are two questions that people would ask, that we would ask ourselves or other people would ask us. No? The first question is, which basic properties are needed for making a material a candidate for a solar cell material? Yeah, and the second one is, what is a good solar cell material? What's now the difference between those two questions? Which one is more complicated to answer? I fully agree, because I mean, the first one is essentially something that one can answer with a physics ontology, right? If we would have one, yeah. So we can list all the different properties that we would expect. For example, something related to electronic structure. However, a good solar cell material has to fulfill way more specifications, right? It has to be stable, it has to be synthesizable, it has to last for some time, it should not be corroded by water. So there are more things, yeah, that are needed. It should be, one should be able to pay for it, yeah. It should not be too expensive, the ingredients that you need to create the material and so on. So while the first one is, again, is just a domain question, the second one is something that spans over multiple domains, yeah. So we did a study on an example, yeah. So there's a paper or a data set published by the Ramprasad, by Rampi's group, the data set of more than 1,000 hybrid organic inorganic perovskites. You saw them already on Tuesday. Volker gave a very cool talk, and I'm actually very happy that he gave this talk because I used it later on even. On these hybrid organic inorganic perovskites, they are made according to this formula you see on the top left, ABXX3. So you have a cation, you have an organic cation, you have a group 4 elements that are cations, and you have these halogen N ions completing them. Yeah, and then you can you see that you can split this up into the many different organic cations that are presented here on the right-hand side of the graph. So now we have to start somehow. So we are on the quest for good solar cell material, right? So we want to somehow define what is good. And one thing is that it should be similar to a known good material. Yeah. One thing that we know, as we know several solar cell materials, 2 are listed here, like methylammonium lead iodide and formamidinium lead iodide. Yeah. Both are known solar cell materials apparently, and we know about them, their densities of states. If we now want to have good candidate materials, we need to find them with comparison. We can, for example, define them via comparison. Yeah? And an approach to do that was presented by the Cotarolo group. You see the citation at the bottom, and this approach is also implemented in the Nomad Encyclopedia. I think this was from Claudia's group. So the idea is that we compare the densities of states, so they are binned, and then Tanimoto coefficients are computed between the 2 bin representations of the densities of state, and we get a value that says how similar they are. Yeah, the higher the value, so it's between 0 and 1. Close 1 means identical. So the higher the value, the more similar the materials are. For this purpose, we kind of limit a bit the range that we compare. So in principle, it's a red box, so from -5 to 10 that is used in the Nomad Encyclopedia. We use a smaller one that is more around the band gap. Yeah. So that means that we essentially compute these similarities between the different systems. Now we have this something like a bit more than 1,000 materials. And by that we get this fingerprint of this comparison of these DOS fingerprints. And then you see here on in the top my nice drawing and this sketch of the Sparkle query. What we get now is a connection between the different individual knowledge graphs. No? I remind you that we have these knowledge graphs of the individual calculation, and we add by an additional study, yeah, that is this computing of the DOS similarities, connections between them. Yeah. So we set them in relation to each other. That is something we need in order to create some sort of a map of materials in here. Yeah, and such a map could look, for example, like that. It's not very easy to spot much here, but let me first explain what the map is or what the plotting is. No? So each material is represented by a node. So when we do such a knowledge graph, we lose a lot of dimensions. Yeah, here we only keep this relation between the different materials. We don't keep information about the material in this representation. An edge is only drawn if the similarity between the DOS is 0.7 or better. So we want to have materials that show similarity to the known good materials, and the colors indicate the modularity. So that means that nodes of similar color belong to the same clique of material, right? And the material. So in this being part of such a clique is defined essentially by the connections between the different materials or the different nodes. Yeah. So by that we can represent the materials that we have, and we see, for example, that here on the top we have grouped essentially only materials that do not contain carbon at all, or in this organic cation. Yeah. Otherwise, this is not necessarily the best representation. Another representation is here. This is a so-called circle pack layout. This is based on a hierarchy of rules in order to essentially place the nodes on our paper plate. Yeah. So the first part of this hierarchy is the halogen atom. Yeah. So we have 4 different halogen atoms, and they are placed in these 4 regions on our paper. As a next level, in this hierarchical placement of the materials of the nodes, I've used the group 4 atom, germanium, lead, and tin. So they are then arranged like that. And similarly, as you see in the top, they are also arranged in the other boxes that represent the halogens. Yeah, is that all very clear? And as a next sorting part, we have these blocked with the organic cation compositions. Yeah? So, and now we already start to learn a few things. First of all, there are more dimensions. So it's a lot of information encoded here. So the size of the nodes is scaled according to the number of connections that end up in this edge. Yeah, the number of edges that end up in the nodes, and the colors again represent the groups these individual ones belong to. Okay, so but we see already a few things, and I'm not an expert in perovskites. If I say things that are stupid, don't be too mad at me. Yeah? But what we see, for example, is that we have for fluoride we have lots of these gray boxes. Gray boxes mean that they have no connection to any other material. Yeah, so they are very isolated. You also see, for example, that there's this position. Now it's really bad that I can point it. Okay. For example, if you look at this position here, yeah, this is always they are apparently always similar. So this organic cation, methylammonium, resides often in apparently in very similar electronic structures or DOS. At least in our view, also in what we get out of the data here. One, of course, has to put this to test in more detail. So what we see here, for example, is we have a way of visualizing material space, yeah, even if it's just a small part of it. And there's nice work by Stefano Cotarolo also on this, yeah. So what we also get out in the end is a table. Yeah, we can have what we have here in the 2 parts of the table. We have the different materials that we have in our study sorted by their similarity to the 2 reference perovskites that we use. Yeah. And now is the point where we, in order to really make something useful out of it, in order to go, for example, from answering the first question, so that is very field specific, to answering a generalistic question. What is a good material for a solar cell? We need more access to more data. Yeah, and access means that it has to be connected in some way. So we need ontological semantic connection to such data, and the data actually also has to be there in the first place. And that is a nice thing that we had Volker's yeah, exactly. These are, for example, things that are missing or information that we could need. Yeah, so we have looked at comparing the electronic structure, band gap, or similarity of the densities of states in the end, but we have not looked into further possibilities or further characteristics of materials that we would need. Yeah, for example, charge carrier mobility, toxicity of material, reliability, or their cost, or simply is it possible to synthesize them? These things have not yet been looked at. And now comes Volker's talk into play. So the first thing, however, is that when we look into toxicity, we could, for example, immediately delete the lead ones. Yeah, but if you have more data, and now this is done by hand, right? This is not done with an ontology, but it could be if everything would be linked in such a way. we see, for example, the two types of cations, this hydroxyammonium and NH2, NH3, are not present in this hybrid D3 database. One could take this as a hint that they are hard to synthesize. Yeah, so there's a lot of experimental data and synthesis procedures. And we also see, for example, that one of the materials here is experimentally characterized, and there's also even a synthesis procedure for that. So that could be, again, this is just to illustrate a bit the idea. Yeah, so at least the system, the material is synthesizable. Okay, so we would have, if we could do these steps also in an automated way in our ontological query, in the Sparkle query, have a way for predictive exploration of material space in the end. Okay, so there are several times when I try to make a fazit here. So ontologies are cool tools. They can help to make data fair, and fair in the sense that the data becomes findable. So in particular, since names, labels, and annotations are clear. And also, what is a nice thing, that synonyms and multiple languages become available. And this means not only languages of different fields, but indeed also different human languages can be there, so make it accessible to more people. That's a nice thing. The accessibility is good because we can do Sparkle queries to get quite easy access to multiple domains, so knowledge from different areas. Stuff becomes interoperable in a sense that goes beyond that I can use things on different computers. It becomes interoperable also because I can link data from different domains and start using it. Yeah. And data becomes reusable because it's well described and we can use it for different purposes. So that's a nice thing about ontology. But the problem is that what we have now on the left part, science, we have some data of materials in some isolated domains. I think electronic structure theory is well said. I mean, there's a lot of data available. But if you, for example, look at the estimated, if one would estimate the size of material space, we are just scratching the surface at the moment. No? And when we do searches, we can only do faceted searches with one-shot queries. So reusing things is not that easy yet. So the fiction would be that there would be more data and a data space that covers more of material space, but also more over the different aspects of material science. So more experimental data, for example. And on the query side, the idea of having well-defined ontologies that are general enough, we could also imagine that computer code, so intelligent autonomous agents, would run our queries, so to say. That we ask a question such as, what is a good material for a solar cell? And such an agent would understand this question and run over the data that is available and find out what is the right material for us to use. I have to speed up a little bit. What I see as a problem is that we have kind of a layer structure in the data that is available, right? On the bottom, you see well-defined and a lot of data in a distinct domain. This is what comes out of the Nomad repository and archive. And then you see larger entities, like, for example, the FAIR-DI project that is going to represent a whole scientific field, so chemical physics of solids, solid state physics. And then even above, there's the STREAM project that you saw in the title that try to have even a larger application area that goes then beyond the nanoscale, also to mesoscale and real device engineering, where you have even broader data. And then on top of that, there's everything else, essentially all the data in the World Wide Web, for example. And this is going to be complicated to integrate. And I think it's important to that when going from bottom up, one needs to reduce a bit the level of accuracy that one uses to look at that. And now, just finally, to satisfy the use of the title, I have STREAM in my title. So one aspect of this STREAM project that is currently going on is exactly that, linking domain-specific data portals to a federated data portal. Yeah, so to make data accessible between different domain-specific data portals. The idea there is to use this DCAT vocabulary. It's a data catalog vocabulary that allows exactly that, linking distant data sources in the end. Yeah, and that would allow for setting up a federated structure via providing interfaces to different data portals in the end. That is just an outlook to satisfy the title that I have. So I'm at the end now of my talk. So I would like to say that with ontologies and knowledge graphs, we can reach exactly that we get really this true interoperability by linking successive research data to some extent. What I mean by that is, whenever I publish a paper, I publish such a knowledge graph, right? I have concepts and data, and this is linked in some way. And when I add on, I use this paper and continue and add, so to say, stuff to it. I kind of put an extra layer around it. And this could essentially also be a bit this question after Marco's talk arose, how to judge the impact of data by the, for example, in the Nomad repository. One could judge it, for example, by the growth of this depending knowledge graph that comes after, that comes essentially out of the reuse of the data. Yeah, but that's a little bit science fiction again. So I thank you very much for your patience with me. I also see that there are questions, but I hand over to the host.
Thank you, Karsten, for this beautiful example of how materials information can be structured, and also how to think of how this can be organized. Let me see. There are various questions.
They are from before.
They are from before. Then let me ask myself while I gear up for the audience to also put their questions in the chat. So if you have questions, please write them down in the chat or raise your hand.
I see a raised hand.
I see a raised hand. I had one question. You have given the example of the perovskites in terms of solar cell materials.
Mm-hmm.
But if you look at these perovskite materials, they were very well known in the field, for instance, of low-dimensional magnetism. Mm-hmm. And also there are many interesting properties that also relate to completely different materials aspects of these compounds. Mm-hmm. So how do you effectively organize this into a coherent system? Do you then have to duplicate all these data in the various domain-specific areas, or can this be organized more efficiently?
Now, in principle, one wouldn't have to duplicate the data. I mean, the idea is to add connections between the data, right? So one of these calculations is part of our data, is connected within the data set, for example, due to the similarity of the density of states. Yeah, but there could be another measure or another connection between the different knowledge graphs, and they can all be stored. The decision is just which of them, for example, I use for such a mapping. Yeah, so I leave out multiple things. I could also make a map where I use the basis set as a connection between data points. That would not be very informative though. Yeah, but there are other more material, also more function-specific measures that could be used in the same way, essentially. Yeah, and the limit for one of them is only due to the fact that I want to represent it. Yeah, so in principle, there can be multiple dimensions for connecting them. Mm-hmm. So okay. That is, at least in my understanding, not the limit. No.
Do we have questions in the chat? Please.
Oh, sorry. Yeah, so it's not completely related to ontologies, but you know, in the same example, okay, I was wondering if you ever tried to use machine learning method, unsupervised machine learning methods, clustering, for instance, to see how that compares to the clustering that you did.
Sorry, that's my time. No, we have not.
Okay, because I'd be curious to see if, you know, what you learn from the knowledge graph brings something more than that, for instance.
But what do you mean?
So,
which type of?
I mean, you have your bins. These can, you can try to find descriptors that would be, for instance, the amount that you have in each bins. Okay, and then you do some kind of PC analysis or TLSNE, and then you compare. You will get a, for instance, a 2D plot, which is based on the first and second PCA components. How does that compare to the clustering that you just did? That's a bit the question.
Yeah, I can't really answer that, because we haven't done that.
But I'm just curious.
But for example, a result of such an approach could still, I think, be represented as a knowledge graph. Yeah. So it's and that's also a thing. I mean, this use of this similarity of the DOS is again just an example to create a number that we can use to make such a knowledge graph, right? The way we do this. This is open. But there are probably also better or other alternative scoring functions, for example, for judging the similarity that one can also get out of a training or a machine learning.
But yeah, the question is, I mean, in terms of also you have some kind of clustering in the end. So my question is more, what kind of new information do you get out of that compared to another method? That's
this I can't say.
Okay, well, I'd be interested to see it.
Okay.
I see at this point no questions in the chat anymore. So let's thank Karsten again. And then we move to the third talk in the session. And the third talk in the session will be given by Giancarlo Guisardi of the University of Twente. And I must say that although we have been in contact in Twente, since we are both from Twente, I think we have never met in person yet, Giancarlo. So I think this is also the time that we should change that. But unfortunately now I'm in Louvain, and you are, I suppose that you are in Twente now. So let's change that. Giancarlo has been working on the topics of ontologies, conceptual modeling, data and knowledge engineering for the past 25 years. He's worked on developing theories, languages, methodologies, and computational tools in these areas. He's been active both in academia and in industry, building reference models in many domains, including software engineering, energy, telecommunication, tourism, healthcare, fiction, agriculture, and various others. And two of his best known results are the unified foundational ontology and the modeling language onto UML. So there are many aspects that Giancarlo will talk about, and I cite two of them because we are heading more towards also a formalistic approach into how to use ontologies also in the field of material science. And these are very deep statements, in my opinion, that I have not put my head around completely yet. But one of the statements will be that data inevitably embeds a theory of a portion of the world. And that is a very deep statement, and I'm sure that you will say much more about this. And the second statement that I also like very much, and I'm also very curious to learn more about, is this statement that the interoperability of FAIR is only possible if our data modeling languages, methodologies, and tools are able to reflect the true ontological distinction in the sense that you've defined previously. So I'm looking very much forward to giving your talk, and the floor is yours.
Thank you very much, Ton, for the presentation. It's COVID's fault that we haven't been able to meet in person yet. Let me share my screen. I hope you can see my slides now. I think this was a good summary of the main points of the talk. So the talk is on the relation between ontology as an area, the area of formal and applied ontology in philosophy, ontologies as artifacts in the sense that Carsten was just telling us, and the I of interoperability in FAIR. Right? So we know that FAIR stands for is an acronym referring to these 4 different dimensions. And I'm focusing here on this it's important to highlight that the definition here of FAIR is recursive. So we say that an information artifact is FAIR if described by information artifacts that follow the FAIR principle. So an information artifact in the particular guise or focus of this talk is interoperable if described by artifacts that are themselves interoperable. And the focus here is on ontologies as these artifacts which describe data in this FAIR context. So what does it mean for an ontology to be interoperable? So first, a definition of ontology that I'm taking here is it's one of the original definitions of ontology, which is a theory about the kinds of entities and their ties that are assumed to exist by an information artifact, by a description of reality. So this is connected, for example, with the philosopher Quine, that underlying any description of reality, there is a commitment to a certain theory about the kinds of things that are assumed to exist. So in that sense, an ontology is not bound to a particular modeling language or description language. So my first point, and then the first takeaway message is that ontology in this sense is completely inevitable. And not only all descriptions make an ontological commitment, but in particular, all information artifacts, which have what is called real world semantics, which not just a piece of mathematics, make an ontological commitment. For example, this is an information artifact, the subway map of Vienna, and this thing makes an ontological commitment to a number of things in reality. So it believes that there are, stations and lines, and there are certain relations between stations in the line and some ordering relations between stations, some intersection relations between lines, and so on. So it commits to a given worldview in which there are these things. There are stations, lines, and relations between all these things. Any information system in particular does that. So if we take even the most mundane information system or a database, for example, this one talking about transplants, this thing believes that there are people and who can be living or deceased, and there are transplants, and there are these surgeons and donors and donees which participate somehow in a transplant and are somehow connected to a person, right? So this refers back to the very first mention of the word ontology in computer science, which comes from a paper by a guy called George Milley, the creator of Milley automata in computer science, in a paper called Another Look at Data from 1967, in which he makes this case that data is a theory about things which exist in the real world necessarily in order to be usable. And data processing is juggling these representations of this theory. And that's an issue of ontology, in the words of Milley, by the way, referring to Quine again. So the opposite of ontology is not non-ontology, it's just bad ontology. You're going to do ontology work anyway, because again, in defining information structures, you are making ontological commitments which are inevitable. So, but it's not just about, the ontological commitment is not just about recognizing the kinds of things that you take to exist, but recognizing what are the possible interpretations of this thing, of this information structure. So for example, there are interpretations, if this model is too loose, right, it doesn't have enough constraints, there are interpretations of this structure which are valid, but not intended. For example, relating this to, I'll explain this by a relation between these two sets. So given an information structure, there is a set of possible interpretations of that model, right? Valid interpretations given the set of constraints which is present there. And there is a set of intended interpretations of the model. And our job is to find in the correct set of constraints that would make the two sets match. So if there are missing constraints, I could have, for example, here in this portion of the model, have a possible interpretation of this model in which there are people who are neither living or deceased, or there are people who are both living and deceased at the same time, for example. Or that there are transplants in which the surgeon, the donor, and donee are roles played by the same person. In other words, I donate an organ to myself and perform the transplant. Right? So this would be a valid interpretation of this structure, but it's not an intended one. So If models are under constrained, there are things in the set of possible things, possible interpretations which are not intended. If the models, for example, are over constrained, for example, if I decide that I will include a constraint here that will define these three things as disjoint, so no surgeon is a donor or a donee, I'm over constraining the model because now a surgeon can never receive or donate an organ, for example. So this is more than I want to say. I just want to say that they are roles which are disjoint in the scope of the same transplant, right? So if I have things which are, I have this situation, things which are intended but not possible, I'm over constraining the model. So the problem here is finding out the exact set of constraints that would make these two things meet. And this set of constraints is the specification of my ontological commitment. So in this sense, an ontology is a kind of contract representing a given worldview, a given conceptualization, telling the world what is my view about transplants and marriages and enrollments and employments and presidential mandates and so on, right? Telling the world which are the interpretations that I find acceptable. In other words, which is my worldview or conceptualization. Now, there is a practical inevitability, so it's impossible to avoid doing ontology work, and it's impossible in practice to avoid dealing with this problem of interoperability. Why? Because all questions that we want to have answered in government, in organizations, in science, and so on, can only be answered if we put together data silos which have been developed in a concurrent, autonomous way. And connecting these data silos is connecting the different worldviews which are embedded in the information structures of these different systems. So the problem of interoperability is exactly the problem of relating these different worldviews. Semantic interoperability, therefore, is a problem of relating these different ontologies, relating these different theories, which are embedded in the systems. It's finding out, for example, the relation between person on the left side and person on the right side. Can I assume that this is a relation of identity just because I'm using the same lexical term? Or transplant on the left and transplant on the right? If not a relation of identity, then what kind of relation do I have there, right? Can I have there? Dependence, what kind of dependence? Historical, existential, generic dependence? If not dependence, then what? Specialization, parthood, what are the possible relations between these things, right? So in order to articulate this possible relations, I need a kind of conceptual toolbox. I need a vocabulary and a toolbox with notions talking about identity, about dependence, about parthood, about causality, about events and participation of objects in events, and such that I can articulate these relations, because this is a prerequisite for encoding these relations in the particular connections between the artifacts inside this information system. So for example, if I know this is a relation of identity, I can code the axiomatization of identity in the representation of this reference in these information systems, right? I know an identity is an equivalence relation and it obeys what's called Leibniz law. So if two things are the same, they have the same properties and so on. But I can only code that, formalize that, axiomatize that if I know it's a relation of identity I'm talking about. So this toolbox is exactly what's provided by ontology now with a capital O. So ontology as an area devoted to developing this domain-independent toolbox with tools for supporting this kind of ontological analysis, right? So it's a 2,400 years old discipline, or that provides theories and tools and methods of doing this kind of analysis. And just to give you some examples how this can get tricky very, very quickly. So take this notion of service, right? This seems to be, I'm going to use three examples which are seem very intuitive. So we seem to have a very strong grasp of the semantics of terms like this. So when we say a service, do you mean the service offering, like Vodafone says that you can hire a telecommunication service for a particular price and certain conditions? Do I mean a service agreement, which is a contract between Vodafone and a specific user? Do I mean the process of service negotiation? Do I mean the process of service delivery? Do I mean the description of the contract, of the agreement, or of the offering? These are all different ontological types of entities, ontologically different types of entities. So the first one is a kind of relational complex, bundles of commitments and claims. So is the second. The third and the fourth are types of events. The fifth one is actually a normative description. What about software? Do I mean software code? Do I mean a software program? Do I mean a software system or a software product? It turns out that these things, the relation between all these things is not one of identity. So for example, the identity of a software code is a synthetical thing. So if I rearrange the code, I modularize, I include comments, I have a different code, but I still have the same program because the identity of the program is defined by the execution class, right? While I can change the execution class of the program and still have the same system because the identity of the system is defined by a set of requirements. It's in that sense that we say that Microsoft Word has 40 years old these days, right? It's not the same code at all. It's not the same class of execution. It's just the stability of a set of core requirements. It probably doesn't even have one single original line of code there. And a product is it's not even that thing at all. A product has to do with those commitments and claims. Again, it's a time of product agreement. So when Microsoft buys Skype, it's not buying code. It's buying the rights and obligation with respect to a base of users. What about person? Do I mean a human being? Do I mean a cognitively capable human being with a legal sense of person, in which if I'm brain dead, I'm not a legal person anymore? Do I mean a legally recognized human being? So the thing that we become when we are registered and recognized by a certain jurisdiction? Or do I mean a legal person in the sense that would include also organizations, so institutions as legal persons, things that can participate in legal relations. These are all different types of types. A human being is a kind, so a type that things instantiate necessarily and that define essential properties of those instances. Cognitively capable human beings is what is called a phase, so it's a contingent type that things of the human being kind can instantiate contingently. Legally recognized human being is, again, a type contingently instantiated by human beings when establishing relations with certain jurisdictions. And legal person in the fourth sense is it's a type that classifies things of multiple kinds, namely the kinds human being and institutions. So we need, again, this toolbox. And once we have this toolbox, we can safely reason, identify, analyze, and therefore encode this kind of relations. This is important when we are putting systems together, because remember, without the proper set of constraints, and therefore with a deviation between the set of possible and intended models, we can have what is called the false agreement. So two systems which intersect in their possible models without intersecting in their intended models. So this is the worst case, the worst problem that we can have with interoperability. It's not a problem if we disagree, it's a problem if we falsely believe we agree. So what is also inevitable, therefore, and that's the point I'm defending here, it's inevitable to make use of ontology in the capital sense, to make use of this toolbox and this series and these methods and this vocabulary for reasoning with how to model things and how to establish distinctions, connections between these different ontologies in the lowercase o sense. Now, let me be a bit fair with FAIR. The FAIR original paper defined these three requirements related to interoperability. I basically touched this one, I2, saying that it's recursive, and this, if we figure out how to articulate these different worldviews and find out how to make qualified reference between these different models, we address this third requirements. But now I would like to come back to this one. So what kind of language do we use to create these artifacts, these ontologies with lowercase o? What I'm defending here is that this task is much facilitated if we have a language that incorporates in its primitives, in its modeling primitives, exactly those ontological distinctions that we use to make those process of ontological analysis, right? So in other words, if we have a language, a modeling language, it's not ontologically neutral. So what kind of language would fit the bill? So the claim is first order logics wouldn't be the case because of its higher ontological neutrality. So logics would allow you, it's neutral in that respect, or much more neutral in that respect, and would allow you to do whatever you want, to describe basically whatever you want. It doesn't impose any ontological restrictions. And it is the same case for OWL, for example, for the ontology, for the web ontology language, because it's basically a subset of first order logics, right? So it's neutral also in that respect. In a sense, the ontology in web ontology language is a misnomer because it has absolutely no ontology in the capital O sense in there. So a language that would honor these distinctions would code, for example, in its syntax and semantics, these ontological notions. It would make a difference, for example, between a kind like person and phases like living person and deceased person, and roles like surgeon, donor, and donee, and existentially dependent entities like transplant, which can only exist if there are entities playing the roles of surgeon, donor, and donee. And would also allow us to identify the relations between these different representations. So I could know immediately that person on the left cannot be identical to person on the right, the types, because they belong to different ontological categories. And the same here, that the event on the left is a kind of event, or maybe a kind of relational complex as well. And event on the right is actually a type whose instance are types of events, saying that surgeons are habilitated or permitted to perform types of events. So the relation here wouldn't be, again, one of identity, but one of instantiation. In the previous case, it would actually be one of specialization. Right? Once we have that model and we have those connections between models, then if the formalization or the axiomatization of these structures can be generated systematically, if not automatically. In fact, from that model, we can generate several different encodings for the model using different formal language, OWL, for example, or first order logics, but other things, higher order logics, and so on, satisfying different sets of non-functional requirements in these representations. Now, one thing which is quite important is that if you have a language that commits to a given ontological theory, what happens, or in other words, a language that breaks with this kind of ontological neutrality, what happens is that immediately patterns and anti-patterns emerge in this language. So the primitives of the language become design patterns as opposed to low granularity things like class or attributes and relations. So for example, if I know that a transplant is an event, I know that an event must have participants, often playing certain roles, that it happens in time, that all its properties are immutable, and so on. So when I instantiate that, I instantiate a cluster of concepts with a predefined axiomatization, a kind of theory inclusion mechanism. I can also identify certain anti-patterns. So if I have something like a transplant, an event in which I have several roles that take their identity from the same kind, of course, one possible interpretation is that the same individual of that kind would play more than one role. And then we can identify this automatically and suggest to the modeler a rectification for this error-prone structure in the model. So just to wrap this up, what I've been doing and my research group has been doing for the past 20 years, let's say, is to develop a foundational ontology, so a domain-independent set system of different micro theories dealing with many of these different ontological aspects, like, classification and taxonomic structures, partial relations, different types of relations, causality, these higher order structures in models, dependence, events, and so on. And then develop a number of engineering tools coming from this theory. So in particular, a modeling language called OntUML, which is a well-founded extension of UML, for example. So it's a version of UML such that the modeling primitives reflect these ontological distinctions and that the grammar of the language has syntactical constraints that reflect the ontological axiomatization. So the language would proscribe from being synthetically correct the models that go against the axiomatization of the underlying ontology. And then we have, computational tools for generating code, again, in many languages, like as I said, OWL, but relational database, Smalltalk, and Java, and many different things. We have tools for formal verification and validation of these models. We have tools for complexity management of large models, and we have tools for learning constraints from the result of validations of these models. So here's the takeaway messages. Real-world semantics implies an ontological commitment. So if we have any information structure and any system which is based in a certain information structure, which has meaning in the original sense of the term meaning, not just mapping a piece of mathematics to another piece of mathematics, but mapping to things in the real world, this thing makes an ontological commitment, and that's unavoidable. Semantic interoperability is about connecting ontologies, because the ontologies are, because of the first reason, ontologies are always there. So your system defines an ontology, even if you're not aware of this, if it has real-world semantics. So semantic interoperability, it's about connecting these ontologies with the lowercase o. And I don't think this can be done safely, that you can have semantic interoperability in critical systems and in critical cases without the proper engineering support, which is ontology-based in the capital O sense. So the slogan is, no ontology without ontology. So no artifact, ontological artifact, no theory about the things you take to exist in a given domain without the support of ontology as this area, this method of analysis. That's it for me for today. Thank you very much. And I'll be happy to take questions now.
That was an impressive talk that you gave, Giancarlo. And basically, I would like to come back to you and ask the same question also to Karsten. Because in your presentation, you made an important statement. And you said that there is nothing like a bad ontology. You only have ontology or no ontology. If I relate this to material science, and it is somewhat of a joke, but I'm very, very serious about this. If I go back to material science, there is no difference between a solar cell material and no solar cell material. All materials are solar cell materials, and the only distinction is between a good solar cell material and the bad solar cell material. Right? I can make any material, not any, but many into solar cell materials, but we are optimizing things. And for this, that seems to be a quite different type of use for ontology than the way in which you are phrasing your ontologies. So let me go back first to Giancarlo. What do you really mean with there is no difference between ontology and bad ontology? It's only a difference between ontology or no ontology. Can you?
Tom, I actually said the opposite of that. What I was saying is that there is, every time you create an information structure that has real-world semantics, you are doing ontology work anyway. So there is no non-ontology. There's just sometimes bad ontology, right? So if you're creating this database of transplants, you are committing to a certain worldview of transplants. So you wouldn't want to have in your database a transplant that happened, for example, before the transplant, the donor and the donee were born, for example, right? Or you wouldn't have in your database a transplant that is performed by the donor. So the donor, the donee, and the surgeon are the same people, right? Are the same person. So you wouldn't want to have that. But how do you know that's bad data? It's an issue in the end of data quality, right? But you can only judge that that's bad data because you have a theory of what are the constraints that exist in the world in the domain of transplants. So you are doing this anyway in building your database and your application and the connections of database and application. You are articulating an ontological theory, a theory about the kinds of things which exist in the world. So you cannot help doing that. But sometimes people, by doing that without the proper tools, they will have bad ontologies or bad articulations of what exists in the world. So there is what you cannot avoid is doing the ontology work. So the opposite of ontology is not no ontology, just bad ontology.
Some related question actually comes up in the chat, because in solar cells, which have been mentioned a lot during this meeting, it is not only about static properties, but it's also about dynamic properties, about transport or response functions. So here in the chat, Rafa Ritz mentions importantly, how do you express dynamic aspects? So events of type A typically precede events of type B, or including the notion of time and evolution.
Yes, that's a very, very important question. So we have in this UFO ontology, one important fragment of the ontology is an ontology of events, which is called the UFO-B, in which we deal with several different aspects of events. So we have, the temporal relations between events. We have causal relation between events. We have this notion that events change the world, mapping situations to situations. You have a mereology of events or parthood of events, which is a particular theory of parthood. We have the theory of object participation in events, and we have a theory about the relation between events and modality, this idea that events only have essential properties. So events are immutable, right? They cannot change in any way. They are changes, but they cannot change, although they can have properties. So for example, a presentation can be exciting or boring, but if a presentation is sometimes boring and sometimes exciting, it's because there are different temporal parts of the presentation which are boring or exciting. So we have this theory of events. And again, this is something which we brought to the language. So this modeling language also has a number of notions or primitives for actually modeling event relations. And again, you can generate code by following this axiomatization. Now, regarding time, if I still have time to answer this, and time is...
we continuously go into the discussion phase. So please, because I think it's very important, let me broaden the discussion, but please continue your answer. But the idea of this discussion is to see how we can optimally use ontology in the field of material science.
Yes.
That is the broader goal of this discussion also.
Wonderful. Thank you. So, for example, when I start doing this, I think the question is very interesting because often in the past, people did not represent at all in this kind of structure models, right? So in the tradition of conceptual modeling or information modeling computer science, events would either appear in separate models like business process models or state machines or things like that, or they were entities which were not first-class citizens in structural models. I mean, we would model operations in all those types, just telling what kinds of things can happen to those entities, but without representing the events themselves. Of course, we need to represent the events because events, they have their own properties. They form taxonomies, taxonomic relations, and all different types of relations, right? So we wanted to take this theory of events that we had and embed this in our structural models. However, once we did that, we realized that would completely change the semantics of the models, right? Because, for example, so if I have this talk, imagine if I include this talk in my model, in my database, right? Once this talk is there, I have to be there because the talk is existentially dependent on me. It's my talk. So what happens to the model is that you immediately move from a kind of snapshot semantics of the model to a historical semantics of the model. And this propagates to the entire model. So this changes these structural models in non-trivial ways. And this corresponds to a particular view of time, which is what's called the growing block view of time. So this idea that time, everything which, so the future doesn't exist, but everything which happened still exists in a sense, although it's not present. So this has interesting implications. So for example, my grandfather somehow still exists because he existed in the past. So he's not present here today, but he can have causal effects in the present. For example, suppose my grandfather was Dutch and I want to apply for a Dutch citizenship based on the fact that he was Dutch. So my citizenship, which is an object which depends on me, is also existentially dependent on his citizenship, but his citizenship is dependent on him. So in order for my citizenship to be created in the present, it has to rely on the causal effect of his citizenship, which must still exist, although he exists in a different form. So this is an example of a non-trivial interaction between taking a serious theory of time and how this interacts with both dynamic and structural aspects.
Thank you. Maybe Patrick, you are also somewhat hidden in the screen. Would you like to comment on this one, also on the aspect of events and evolution of time?
Maybe I will just take up something else, which I think has some relation to this. I've heard sometimes somebody say that there are different kinds of people working with ontology. I've modified a little bit. Said first, there are the philosophers. I think Giancarlo is one of those. Also, Achille FAIR-DI and Nicola Guarino are people in this field, where the idea is mainly to represent the real world and really look at all these ontological commitments. And I think what Giancarlo is telling us here is very important. And it helps us when we are developing upper level ontologies so that we understand what is really going on. And I think in the material science field, you see people from EMO are trying to do this. The second kind of people are the computer scientists or maybe knowledge representation people, which probably I am part of, where we are mainly interested in knowledge representation, which kind of languages can be used, which kind of constructors to represent things like and, or as a logical constructors. And we're interested in, depending on which constructors you use, what is the complexity of the languages? So how much time will it take to do reasoning? And then there are the application people, the domain expert people, for instance, material science people, who actually don't care of any of this. They have an application in mind and they just want it to work. And they don't care what how it is represented and what the connection is to the real world, maybe. Now, what is interesting there is that for the computer scientists and for the philosophers, it may be interesting to know what are the tasks. So if you want to use ontologies in material science, what are the tasks that the application people need? For me, it is search and integration. That's what I'm working on. But it may be other kinds of things like defining similarities, clustering different materials, where you also could use the ontologies, for instance, in ontology-based machine learning. So for getting back to the events and time, I think what Giancarlo is telling us here is interesting for definitely for the upper level ontologies to which we can connect our own ontologies. And oh, I lost it. Okay, I'll stop there.
Yeah. Thanks, Patrick. And maybe also Karsten can give his worldview on this.
If I can comment very quickly, I basically agree with everything that Patrick said. I think these are indeed three different areas of concern. I think they are strongly connected. I'm myself not a philosopher, although I do a lot of this work with philosophers, but I started my career as a protocol engineer, implementing network protocols and working with process algebras and things like that 25 years ago. And I just thought it was extremely useful to look at this tool. So I think I'm between the two groups, Patrick. I'm very concerned about these ontological things in the philosophical sense, but I'm obsessed with creating engineering things and testing applications. But I fully agree with you with the characterization.
Then I give the word to Karsten to give his view on this topic.
Well, I'm not sure how qualified my view on the topic actually will be. But what I see as a problem in let's say of acceptance of this ontological approach in the field is that it seems like a very long run until one can actually get something useful out of it, right? So it's like walking through a desert is a bit, and the oasis where we get then the cool results is a bit distant, yeah. And also I think technically, what I find a bit annoying, for example, is that I can't really do a calculation with an ontology, right? I mean, many of the properties that we find interesting are derived properties. So the ingredients are there, yeah, but I still need to use at least in my understanding, an external tool to do such a analysis computation. So I think we are discussing a lot about very complicated high-level things, but some of the practical things would also be of interest for the community. So it's I think it easily gets a bit too philosophical, I would say.
Can I comment on that?
Please.
So you know, how can we decide if things are too philosophical, right? I think they are extremely practical, actually. There is something that Patrick mentioned, this idea that, for example, my concerns are about modeling the world. I would like to emphasize that I don't think the role of ontology, even philosophical ontology, should tell people how to force people to agree in a certain worldview, right? I don't think that's possible. I think people look at domains with different interests and in different granularities and so on. What we want to do is to provide tools that would help people to have a consistent view within their set of choices. So a kind of intra-worldview consistency and inter-worldview interoperability. So you model your thing in a consistent way and find out how your worldview relates to other worldviews. So it's not about being normative in the sense of telling people how the world should behave, right? Although some philosophers do that. I think it's extremely practical. So if you find out, for example, if you have a small theory of events, this theory of events with its axiomatization becomes a kind of design pattern. So every time you have to model events, you just reuse that thing and you guarantee a certain uniformity of both modeling choices and axiomatization. You can, you know, it's like a pattern language. Sometimes you're going to include or exclude some of these axioms. So there are several, let's say, variation points, but you can reuse the bulk of the theory. The third point I would like to mention is that on calculating with things, there are different calculations I want to do with things. So for example, one of the mappings we have from this ontology, from this modeling language onto ML is to a language called Alloy that allow us to do model finding, type of visual model checking, right? And this is extremely useful for doing validation, which is very different from verification. So if I map this to DL, for example, this allows me to check satisfiability and a number of properties of the model, consistency and so on, but it doesn't help me much to check. So it allows me to check if I got the model right, but not if I got the right model. And validation by visual simulation can help you to do exactly that. So what this tool does is, for example, once I have that model about transplant, it's generating all logical models of that specification in a bounded context and so on, but a finite set of models. And one of those will be one in which I'm playing all these 3 roles in the transplant, right? Or that someone is playing 2 of these roles in the transplant, and so on. So there are different calculations we want to do, and this with different non-functional requirements. Sometimes I don't care about decidability, for example, at all. I just want to do different things with do different calculations, and this would require different language. But the conceptual understanding should be, I think, in my view, common to all these mappings.
Let me add my own perspective on this one, because I had been working on both solar cell materials and on these organic, inorganic hybrid systems, of which we've seen so many beautiful examples of, for many years. I have never thought that these materials would become solar cell materials. So if the ontology of this class of solar cells would have been correct, I should have known 10 years ago that these are important for solar cells. And I mean good solar cells, not the bad solar cells. And I missed this completely. So in my view, ontology would help also to see which materials are useful for which properties based on a larger database than just electronic structure calculations. So this was the reason that I also gave the examples that I gave in the beginning. I think symmetry is a perfect ontology. It is defined, it is clear-cut, it's easy. But materials are infinitely complex with infinitely many possibilities. So then the question is, how do you use an ontology properly? Of course, you can use it to optimize a property, but also to see if materials that are developed in one area of research could be useful for catalysis or for anything. My personal statement, at least. Patrick, could you comment?
Yes, I agree with that. I can also comment on Karsten. I give a slightly different answer than Giancarlo because I interpret computation in a different way. So what Giancarlo was telling is about ontologies and the computation that you can do with the ontologies. And I agree completely with that, because the ontologies are somehow a representation of knowledge. Now, if I would interpret Karsten's question as computations related to materials, then this is not what ontology would do. They don't compute these kind of things. The computations are about knowledge. So what you would be able to do with the calculations is to represent knowledge about these calculations. You could represent which kind of method you used for this calculation, connect these to other kinds of methods, connect to different kinds of methods that have been used to calculate the same kind of property or of different materials and so. So the computations for material science are maybe not the things that you will be able to do with ontology, but you can represent knowledge about these computations. And then the computations that you do for the ontology are the ones that Giancarlo talked about, talking about, for instance, validation and consistency and so.
Karsten?
What I try to refer to is, in the end, the idea of, I mean, I do query using Sparkle as a language, so to say. And it would be super cool if I could do a little bit more complicated math in Sparkle. Yeah, if I could do such a thing, like we have this this Tanimoto coefficient. If I could compute such a thing as a Sparkle query, that would leave one step out that I have to do otherwise before. Yeah, that's just a practical thing. Yeah. But I understand that it's probably beyond the tool. So, and it's okay.
Well, you could imagine that you have information in the ontology about this coefficient, and sorry, You have information about the provenance information that I talked about before, where we would store information about which exactly algorithms or which tool that you've used. And maybe you can store information about the code there.
And that would exactly go towards this. I mean, I had these two questions on this one slide, and the last one was the complicated one. And if you would imagine like an agent that could then use the ontology in order to find the right way to compute the similarity between two of these densities of states, for example, then I could then I could have this computation that I would like to have. It's just apparently hard to implement that or have that.
So actually, this is very much connected to the original vision of the semantic web, which was proposed in 2001, where the idea was that you would use ontologies, and you would use knowledge representation languages where the databases could represent what their capabilities are. So what is the content that they have? For instance, this database is about this kind of materials. It has these kind of properties stored, and these are the relations between these properties. And then you would have agents, exactly, that when we have a query or a need, would actually try to figure out which of the databases to use, translate the terminology that we have used for the query to the terminology of the databases, get partial results from the databases, and then merge this into a full answer to the question.
I mean, you referred to this was the initial idea, and this was in 2001. So my question would be, is it realistic? Also, could this happen, or was this just a fantasy in the beginning?
I think a first step has been made to this by, for instance, the biomedical field. Quite many of the databases there are annotated with ontologies, and this makes it easier to find which databases you need. To get information in the databases, there are some databases that allow you to actually use the ontology, click on terms, and then immediately send a query to the database with the ontology terms. So steps have been made in different fields towards this, but the full vision has not been realized. That's clear. And the vision of semantic web was actually redefined a few years ago, where there's more of focus on a web of data, where ontologies are still important as the way to structure the data, but more focus is put onto data on the web that is linked in different ways.
In view of the time, I would like to end the discussion here. I would like to thank Patrick, Karsten, Giancarlo very much for their contributions today. Appreciate it a lot, and I'm sure that there will be much more to come in this field. And let's give them a big hand and applause from the people here in Louvain.
Thank you very much. It was a pleasure. Thanks for the invitation. It was great interacting with you all, with Patrick and Karsten and so on. Hope to have more opportunities in the future.
Raphael Ritz.
Sorry, I just wanted to click applaud and I accidentally raised hand. Sorry.
We need a different nature then. But Raphael, thanks also for your contributions. And then we reconvene at 2 o'clock. We reconvene at 2 o'clock this afternoon. Thank you.
So hello everyone and welcome. Sorry, it's me. Okay. If I manage. Yeah, no, but it's me. Okay. Now it should be okay. Sorry for that. So welcome everyone to our afternoon session, which is dedicated to exascale computing. As I indicated yesterday, our chairman unfortunately cannot make it for medical reason. And so we've shifted the whole session by 15 minutes. So we're going to have 3 talks, 2 that last 45 minutes each. And then we'll have a coffee break of half an hour. And then another 45 minutes break. Another 45 minutes talk. And then the final discussion. So the 2 first talk are going to be by Erwin Laurer from the Max Planck Computing Data Facility, of which he is the director. Then the second talk is going to be by Matthew Smith from the Barcelona Supercomputing Center. And the final talk is going to be by Bert de Jong from the Lawrence Berkeley National Laboratory. So Erwin, the floor is yours. You can share your screen.
Okay, thank you very much for the nice introduction. I hope you can see my screen and now also in full screen mode.
Yeah, we can see the screen in full screen mode. Thank you very much.
Perfect. Excellent. So then, good afternoon, everybody, and thanks a lot for the opportunity to give you this presentation here. As was said, I'm the director of the Max Planck Computing and Data Facility in Garching. And I would like to talk and give a little perspective where we are with respect to exascale computing, what are the opportunities, what are the challenges. So changing focus a little bit from data that we discussed over the past couple of days to a little bit more computing, although data will also not be forgotten in this talk. This slide shows the development of the supercomputing systems in the world over the past 30 years or so. And as you see, there is a straight line going up, a clear trend where systems are going. And that trend actually means that we should reach the exaflop now, or should have reached it last year. And in fact, first systems are being planned to become online, maybe even this year in the US, or certainly next year. So these will be enormous systems that provide 10 to the 18 floating point operations per second. So this is really a new era of high performance computing that we are entering here. But this doesn't come for free, right? It's not just, oh, there is a trend line and technology is following this trend. There has been a lot of work spent to actually reach this milestone. And this work reaches back to the year 2008, when the first very influential study by Peter Kogge and all has been performed in the context of DARPA. And that really laid the groundwork for all the technology development that we've seen over the past 10 years or so in processor technology, memory technology, interconnect technology, and so forth. Now, while this is clearly a major technological milestone, and it's great that we can build those systems, we need to build them for a purpose. And there is actually many applications that benefit from the availability of such large systems. There is 2 publications that you can look at. There is the Praise Scientific Case from 2019, and also in Germany, the Gauss Center for Computing has issued a strategy paper that basically shows how different scientific domains can profit from the availability of such large systems. And it's clearly the usual customers of high performance computing, like the fundamental science, astrophysics, particle physics, cosmology, the whole weather, climate and earth science areas and so forth, the energy area. But there's also a lot of life sciences that is now using high performance computing and increasingly using these large systems with advances made in bioinformatics, the new microscopy and imaging technologies that you have in structural biology and neuroscience and so forth. And clearly, although on this list relatively down, I don't know about the ordering here, it's random order, but material science has always been one of the major users of high performance computing systems and is probably also now one of the first ones to actually use these large systems. And as we are discussing in this workshop here, it's not only the simulation, but it's also the data-driven material design that drives the field. And in the past couple of years, we've also seen a new trend, which is actually changing the field a bit and adding even more computational requirements. And this is the advances that have been made in artificial intelligence, machine learning, deep learning, and so forth, and where we will see convergence between simulations and machine learning. Now, a key problem on the technology side that we face is that the so-called Dennard scaling actually has ended. So many of you know about Moore's law, and that basically says that every 18 months or so, you can double the amount of transistors that you can cram on a certain area. And this orange line here, I don't know whether you see my pointer, but the orange line on top that goes still straight up, this is actually Moore's law. Yeah, and Moore's law has basically also meant that with new generations of processors, the processor speed was going up, and that was the so-called Dennard scaling. But that came to an end about the year 2000, when you could not actually use more power to get an even higher frequency of your chips. That means that the single thread performance basically saturated, and people had to increase the number of cores, they had to increase the number of active computing elements in whatever form to still get more speed out of the processors. And that basically meant that the processors became much more complicated and the systems became much more complicated. And that we see now also in the systems that we see today. Today we see three dominant architectures, meaning coarse-grained ways how you actually put together and assemble a large-scale systems. And I'm giving you 3 examples from so-called pre-exascale machines. These are machines that have recently been installed and are not yet exascale, but in the size of several hundred of petaflops. The most simple, in inverted commas, because it's not a simple machine, simple ones is so-called homogeneous machines. This is basically machines that are built of one CPU, and across the whole system, you have the CPU and nothing else. So from a principal point of view, it's the most easy one. This is what Riken is doing with the Fugaku system, that is basically just, again, just in inverted commas, a collection of a large number of ARM chips made by Fujitsu. When you look a little bit into the details, you see the situation is not as simple. It's not a standard many-core system, but it's really one many-core chip is actually composed of 4 different chiplets, 4 different areas that have different memory characteristics and so forth. So it's, again, it's not so easy to deal with it, and you have to take care using it. A very predominant way to build systems is so-called heterogeneous systems, where you still have CPUs, but you use GPU technology that is widely used these days in high-performance computing to actually accelerate them. So you have a heterogeneous node consisting of CPUs and GPUs in different quantities, but then you build a kind of homogeneous machine out of those node types. And this is the way that the US pre-exascale systems, particularly Sierra and Summit in Oak Ridge and in Lawrence Livermore, have been using, and you see a diagram here to the right, how the system looks like. It's quite complicated because you have two processors. In their case, it's a power processor. With each of the processors, you have 3 GPUs. You have the standard DRAM associated to the processor. You have high bandwidth memory associated with the GPUs. And you have the different network characteristics across the whole thing. And then you have this in a couple of thousand times in the system, right? So again, it's again a quite complex system. And the third approach is actually combining the different characteristics. This is what is the so-called modular concept that was first prototyped actually in Jülich. So Thomas Lippert, who was supposed to chair this session, is one of the guys who was first thinking about that concept, that you have different modules that can be heterogeneous, homogeneous ones, and that you combine in an integrated system. And one of the European pre-Exascale systems, Lumi and CSC in Finland, is one of the systems doing that. And I'll talk a little bit more about that system in a minute. When we then look what will be the Exascale systems that are coming up, the most firm plans are in the US, and most likely Frontier will actually be online this year. You see that these are heterogeneous systems. So all three are basically made out of heterogeneous nodes with CPUs and GPUs, and then you link together thousands of these nodes. Both Frontier in Oak Ridge and El Capital in Lawrence Livermore, they use AMD technology. So they use the EPIC CPU and the AMD GPU, while the third one, which is Aurora in Argonne, is actually using Intel technology. So this will be the next generation of the Intel CPUs, the Sapphire Rapids, and the Intel GPU. And I highlighted here already one of the critical points that we see in using the systems, that the programming environments, they're very different. So Intel is pushing what they call one API. So this is their programming environment. And as the name says, it's neither one and it's also not an API, but it's a collection of different tools. While AMD is using their Rockham programming environment, HIP, which is very close to CUDA actually, to use the GPUs. So there is really a little war going on between the big vendors on how to most efficiently and best use their systems. And that brings me to really the challenges that we see, right? So these systems are enormous. We have to live with an enormous level of parallelism. To reach an exascale kind of performance, you need the order of 10 to the 9 floating point units, right? And those floating point units, they should be kept busy. We have to live with increasing heterogeneity, right? I've already shown you a little bit about that. We have the CPUs, the GPUs. We have potentially other accelerators, FPGAs, and people are thinking about neuromorphic chips and even further in the future, perhaps even quantum chips and so forth. And you also have heterogeneity in the memory hierarchy. You have high bandwidth memory, you have solid state, NVMe, the storage is changing, you go more towards object store. So there's a whole change and complexity actually in the hardware. And this is also reflected in the programming environment, where we do have the kind of standard MPI and OpenMP for distributed memory and shared memory. But then there's, as I said, there's a huge fight going on how to actually use these accelerators. Is it CUDA? Is it HIP? Is it one API? Is it OpenACC? It's not yet clear where the mainstream actually will be going and who will win. And that actually means a lot for performance portability, right? It will be very difficult to port systems, applications to the systems. Then, of course, as these systems grow so large, there is a chance to actually do novel methodological approaches and even novel numerical approaches that so far have not been feasible. And for some algorithms also there is an inherent scalability limit, so you need changes in the numerics and in the approach to actually use those systems efficiently. And finally, we are starting to see that we're not only looking at one simulation that is being executed on the system, because, as I said before, scaling applications to this enormous size is often not really feasible. But we have a more integrated look at the workflow that an application actually is using, where the simulation actually is only one part. And I have a picture here again from Jülich Supercomputing Center on Earth system science, where the Earth system data is being used to do the simulation. You have data analytics, you have visualization, you have AI components, and so forth. So that needs a lot more than just running a single simulation on the HPC system. And this picture shows how complex it really can get. This was a kind of artificial scheme that was developed by the ETP for HPC. That's an industry group in Europe working on HPC technologies. And that basically thought, how would a block diagram actually look when we put everything together? And this is kind of systems that are being built today. So you have, on the top, you have the data sources, yeah? That can be conventional data sources that you have available in files or so, but increasingly we also see streaming data sources, like from IoT devices and from other sensors and instruments. They need to do data pre-processing, data cleaning before you can do your simulation and analysis, right? And then you have the data post-processing, again, going into files or back to the devices, going into a loop here. And when we look at the simulation and the analysis, then very often nowadays uses AI technologies to actually do online steering to optimize the system. So there is actually a teacher loop involved where you modify and train your artificial intelligence system, and then that actually interacts then with the simulation. So the proper simulation only becomes one small piece, an important piece, but a small piece in this whole loop, and building these whole loops actually is yet another challenge. So we've been doing these kind of things to some extent so far on standard systems as we use today. But one problem we see here is that we use the different modules and think of these different things here as the simulation, the data analytics, the AI, and so forth. And we kind of map them on the architecture that we have available. Yeah, but the architecture is kind of, or try to be as generic as possible, which means that it's not really suited for none of these different tasks. So when we go into modular systems, into composable architectures, then we try to have different modules that are tailor-made and specifically configured for certain tasks. So you can actually do the task you want to do on the appropriate system. And but the different parts, different modules of the systems are tightly interconnected. And this is like the LUMI system, what it's doing, but also other existing systems are going in this direction. Like the systems we have in-house, we have a large GPU module that is used for applications that can make use of GPUs, but also a large CPU only homogeneous part that other applications or other parts of an application can be using. So where is Europe going in this whole thing? I've been talking about US systems quite a bit, but not so much about Europe yet. And Europe has been relatively late in this race. But fortunately, in the mid-2010s, Europe understood that they need to get their act together and start investing heavily in order to stay competitive and not being overrun by US, Japan, and China. So starting in 2018, a so-called joint undertaking, that's a special form of European financing, has been created, which is called Euro-HPC. And all European countries are actually now taking part in this joint undertaking. And this joint undertaking really has three pillars. On the one hand, it builds an infrastructure and operates an infrastructure. So Europe itself now is actually buying systems and operating systems. I'll show you a little bit about that. And it's also investing in related research and developments, in applications, skill development. And by that, building a real European HPC ecosystem. A cornerstone of the European endeavor is actually to build a European processor. So there has been a lot of discussion about digital sovereignty and sovereignty in high performance computing. And so far we are basically buying US systems, right? Or maybe sometimes Japanese systems. But while many components are actually also available in Europe, Europe is lacking processor technology. And so as of 2018, there has been a very large project started, the EPI, the European Processor Initiative, that is has the aim to develop a truly European processor technology. And this project is following two streams. On the one hand, it builds a kind of classical CPU that is ARM-based. So it will be very similar to the Fujitsu GPU that is currently available in Fugaku. And if their plans pan out, then the first version of that chip should become available next year, and then hopefully being deployed in large-scale systems later on. And then for 23, they are planning for the second generation that comes then 23. And this the code name of this chip is REA and REA 2. We'll see how that works out. There is a second stream, which is a little bit more risky and more on the research side, that is exploiting the RISC-V architecture for these chips. And the idea is to use this first as an accelerator that should then together on with the ARM chip be deployed on an integrated chip, and that should then eventually become a full RISC-V based CPU, but that's a bit more long term. So that one of the pillars is that Europe actually deploys systems, and last year they have actually this year they have started to buy 3 pre-exascale systems. And the 3 pre-exascale systems are in Finland and in CSC, in Kajaani, in Bologna, and in Barcelona. The systems in Finland and in Bologna are being deployed now. In Spain, they are still in the procurement process. And they are buying also smaller petascale systems on the range of 10, 15 petaflops that are spread around Europe to really build the second tier, so to say. And this pyramid will then be complemented in the coming years with 2 exascale systems, most likely to appear 24, 25. If things work out okay, then next year the process will start to decide on the hosting country for these exascale systems. So let me show you the two existing pre-Exascale ones. First one that is LUMI, that's a Cray EX system, or now HBE. That's a very large system with over 500 petaflops peak performance. That's being installed in Finland, in Kajaani, by CSC. And this is one of these modular systems, right? You've seen this wonderful snowflake already before. And that basically shows that you have these different modules, right? Most of the performance comes through a GPU partition, yeah? And again, they will be using the AMD GPU technology. They will also have a partition that is a standard x86 partition. We'll have specific partitions for data analytics that also has then accelerated storage. You have your standard parallel file system, you have object store, and you potentially will also have emerging technology and all that on a high-speed interconnect. So this system is currently being built. I think the x86 partition should already be available. The GPU partition is expected to come next year, and that will actually make this one of the largest systems in the world then. And a similar approach is being taken by the Italian system called Leonardo. They also have this kind of what they call a booster module. Again, this is many GPUs. In their case, it is the next generation of the A100. So meaning also that this will be coming next year from NVIDIA, and that will provide the majority of the performance, the 240 petaflops. And then they have a 9 petaflop standard CPU module, all interconnected to the same high performance storage. And then you have the various other services for visualization and so forth. Now, these systems actually, in order for them to be used very efficiently, a lot of effort needs to be spent on applications. And Europe has, starting with 2015, also started to invest heavily in application development. And they have started a program called Center of Excellence, which are large-scale projects that push the boundaries of important applications, or in general, the usage of these exascale systems in certain domains. So we have 14 of these centers of excellence at the moment. And as you can see here, this Nomad you have already heard, and I will also talk a little bit more about that later on. That is specifically for materials discovery. There's a second materials one called MAX as well. And T-Rex is also looking in similar technologies. So this is a truly pan-European network. It spans many different domains, from engineering, medicine, climate, materials, I've said, combustion engineering, and so forth. And as I said, Nomad is one of them. And we've actually had 2 phases of Nomad, or one phase is finished and the second phase has just started in 2014. And one big achievement, of course, is the Nomad repository that you heard during this week a couple of times. So I'm not spending time on that. But the second phase now that has started a few months ago is also then looking into the exascale developments. So there is development of exascale codes, of workflows that combine the different components, as I've shown, and also data analytics. And all these developments will then be demonstrated with use cases from urgent energy and environmental research. The big problem is that if you want to go to from a petascale to an exascale system, you need to, or you have suddenly a factor of 1,000, right, in performance that you should be using efficiently. But how can you use a factor of 1,000? You're not going there in one go. So I'm showing you now from a other center of excellence in biomolecular research called BioExcel, an example and a related code which is called GROMACS. It's a classical molecular dynamics code. And basically, what they want to do, they want to split the problem, right? So, of course, they want to improve the code performance and the scaling single simulations, right? But they would be satisfied if they can get this factor of 10. And then they combine in single jobs already functional ensembles, yeah, that you combine. And if you speed this up by a factor of 10, you're already at 100. And then you run many of these workflows in so-called ensembles. And that can give you a factor of 1,000. But you see, you have many different levels of parallelization that you need to think of, starting from the small vectorization inside the CPUs, the vector extensions that you have, the usage of the GPUs, the domain decomposition, and the ensemble decomposition. So it's really a full-fledged strategy here. Now, let me spend the remainder of my talk in giving you a few examples of what we do in the Max Planck Society, and specifically at my institution, the Max Planck Computing and Data Facility, of which you see a nice picture here. So this is actually where our systems are, and this is where our people are. And show you a few of the things we are doing and the successes that we have achieved. We have a very large application group that works with leading software packages and the researchers, mostly in the Max Planck Society, to actually scale them, make them better, port them, and so forth. And there is a lot of materials and biosciences. We have also an Eigensolver library, but we also deal with astrophysics, plasma physics, biophysics, bioinformatics, a lot of different things. And when you work with codes, you have to deal with the complexity that I've showed you in the beginning. So we are really dealing with all those problems. We use MPI and OpenMP. Important here is really that you use most modern things, modern OpenMP, shared memory MPI. You use CUDA-aware MPI, meaning that you can actually communicate between GPUs and you don't have to go via the host all the time. You need to work with the SIMD intrinsics, with vectorization and so forth. Programming the GPUs, CUDA, OpenACC. You need to use task parallelism. We use AI frameworks and also go into a little bit more researchy directions. That one is the usage of performance portability frameworks, particularly in the US ECP, the Exascale computing project. There are such frameworks like Cocos or Raja being developed that actually should provide an abstraction and independent of the hardware, provide you with good performance. And we're also looking into things like mixed precision fault tolerance and so forth. Now, this is one example that from a plasma physics simulation code that just shows how if you spend enough effort porting it to GPUs, you can really get tremendous speed up. The high bars, this is the CPU version, and the low bars are using the GPUs as well. As you can see, we get a speed up of 10 to 15 using the GPUs versus a CPU only. This was run on Summit, the system that I've shown you in the beginning, one of these US Exascale systems, and it scales pretty well. This is weak scaling, pretty well up to 512 nodes. So we're using 3,000 GPUs in parallel here, so which is quite an achievement. But far from Exascale, but quite an achievement. We're doing similar things also on electronic structure code. This is a DFT code Octopus that some of you might be familiar with. Here we were able to use it efficiently and up to 32 nodes. This is our system where each node has 4 A100 GPUs. You see a speed up to the CPU version of about factor of 10, again, which is very good. And so this is really something that you can use in production today on today's systems. So I mentioned a big effort for us also is an eigenvalue library called ELPA, which has become a de facto standard for electronic structure calculation. It's better than most of the commercially available softwares. It's open source, was developed in a collaboration with the Fritz Haber Institute, the Technical University Munich, Wuppertal, and the MPI KTS. It has very good scalability. So this is up to 40,000 cores on our CPU system. Of course, it depends a lot on the matrix size, right? If you have a small matrix size, then of course you cannot get the best performance. But we've also shown this using it up to 200,000 cores on the Argon system Theta. And this library is also part of the efforts in Nomad that I mentioned. And here we're working particularly to move it to GPUs. So now we have full support of NVIDIA and AMD GPUs using CUDA and HIP. We're also working on the One API so that we can use it on Intel GPUs once they become available. And we have actually demonstrated this at scale, of course, again, with a huge matrix, 1.8 million. And we're using about 24,000 NVIDIA GPUs on the Summit machine, which is a large fraction of Summit, very efficiently. It was most likely a world record, I'd say, but it's not proven. And we're also working and have been porting it to the ARM vector instructions so we can use it on Fugaku, on the current #1 machine in Riken in Japan. As said, we are experimenting with this performance portability frameworks, Cocos and Raja, and we get so they're certainly production ready. We can use them. They still have some performance problems, right? You see there is still quite a difference, particularly when you look at the GPU versions, and we are working with them to figure out what the reason is and how we can make them better. So message basically is you can use them, but if you need the best performance, then it's probably they are not there yet. And a new stream of research we've just started together with groups from plasma physics, Frankienko's group on a gene 3D code, is to use mixed precision. So we are typically in scientific problems, we are using typically double precision. But of course, it's maybe not always necessary to use double precision. We kind of used it as a means of convenience, yeah? If you can use lower precision, then on the one hand, you can double the performance of vector units without doing anything, right? And you're also reducing the amount of data communicated. So we looked at the gene 3D code to figure out what does it mean to use single precision instead of double precision? Are we getting still the numerical results that we expect? And in the problems that we've evaluated, we see actually a good numerical precision, even with single precision. So it's reasonable what we are doing. And we can get a lot of speed up. So some parts actually almost 50% speed up. Overall, each time step of this code is about 35% faster, which is quite an achievement. These are only initial results. So we are having further plans to do this in more detail later on. And we also looked at using single precision in ELPA, in electronic structure codes. Here we used it in the diagonalization inside the Picard type iteration. And So here you see that the numerical precision in terms of the number of SCF steps. And depending on the matrix size, you see that certainly in the earlier iterations, you can tolerate lower precision. You're not losing any of the accuracy. At some point in time, then of course, you're not having the precision anymore that you need, and then the results are not valid anymore. But so you need to take care when you use single precision and really figuring out where you can use it. But if you can use it, you can get quite a speed up. Here we get a speed up of 1.6, right? So this is something that certainly is worth looking into, particularly as we get a lot of hardware that is very well suited for single precision or even half precision, like GPUs that are mainly made nowadays for AI problems that basically use single precision. So with this, let me come to my conclusions. The exascale systems are here, basically, right? You can't get your hand on today, but in a couple of months, you will be able to run your first jobs on them. And so they provide really a lot of opportunities, a lot of great science that we can do on these systems, and material science will for sure be among the leading ones using them. But we have to live with more complex hardware. We have the different CPUs, accelerators, memory hierarchy, and so forth. And we have to think of not only a single simulation anymore, but really about more complex workflows, different simulations, data analytics, AI, handling of large data, sensitive data sometimes when you are in the biodomain, for instance. And that means that we need effort on all levels. It's not only building the machine, which is of course a huge effort, but we need a lot of efforts in application support and maintaining and improving applications, and also the associated data solutions. And fortunately, there are projects on the way, doing that. The Euro HPC joint undertaking in Europe, certainly the ECP in the US, and Nomad is one of these efforts here in Europe as a part of the Euro HPC joint undertaking. Thank you very much.
Thank you, Erwin. Are there questions within the audience or in the chat? I can start. So you highlight in your conclusion the importance of workflows, and I'd like to relate that. Well, you illustrated that with the case of GROMACS, where you were showing that in the factor of 1,000 that needs to be achieved, a factor of 10 was kind of related to the workflows. And I wanted to understand a bit more, is that independent jobs in this workflow? And if I can relate that, how do you see high throughput computing in this respect?
This is this is always the $1 million question. These are independent jobs indeed, but the results are tightly related. So you need to collect the results together, and in order to progress. I'm not an expert in molecular dynamics, but this is how they explained this to me. Now, I think this whole idea between high throughput differentiating between high throughput computing and high performance computing, I think these days is a non-discussion. We should talk about large scale computing, right? Because at the end, we have large systems and we have large scientific problems and we want to solve them. So we need to make the best use out of these systems. And the discussion goes back to the time when actually a dominant part of the cost of a high performance computing system was in the network. And this is not the case anymore. And even if you are using high throughput computing, you need a good network that you can use your data, you go to your disk systems and so forth. So I think, to me, it will be, the use case will be to have ensembles of maybe not so tightly coupled ensembles on these systems. Otherwise, we'll not be able to use them. I don't see single simulations really scaled up to that scale.
Thank you very much. I see that Matthias has raised his hand.
Yeah, so some extent, I have two questions. So one was somewhat similar in a sense. I think it's good to see that exascale computing does not necessarily mean that your individual code runs on exaflops, but that you can do this by workflows, and that's good. Of course, at the end, also in your case of the GROMACS, means that some jobs will finish a little bit earlier than other jobs. So there we also need some on the operating system or on the computer system level, some way that these jobs then can be used for other calculations, right? Or these CPUs can be used for other calculations.
Correct. Yes. Mm-hmm.
But I think that is a good thing, and that would actually serve also the material science a lot. Now, I have two questions really. So one thing which we had in the very early time of high performance computing is that you could calculate a lot of data, but then in fact getting the data on the hard disk took another day. So how is that nowadays actually in the communication issue?
The communication issue is still there, but people are building different layers of I/O hardware. I'm now trying to find, yes, here is the picture of the Summit system. Mm-hmm. And as you can see, you have the processors and you have your network interface card where you actually go also to the storage. And you have a little box here, which is an NVMe. So that's a non-volatile memory. So the systems have a deeper memory hierarchy. So you have buffers that are close to the computation that you can use for that. Mm-hmm. And that's one way to deal with this I/O problems. There is actually a project I haven't mentioned, a EU project called Admire that has recently started that is looking into this, looking into how to use these NVMEs, how to combine that with scheduling. So if you have, for instance, data still sitting there, that you can actually get your next job to this, going to the workflows, for instance, right, that we were discussing. But we also have to think of we have basically to think about data reduction. Yeah. Mixed precision is one way, for instance, to go there. We have to think about data compression. We have to think of what do we really need to write out to the disk system? What can we keep in memory? In situ processing, for instance, is one of those keywords that we use here, where you basically try to do your analytics, again, in a workflow kind of scheme on the same memory where the simulation is using the data instead of spitting it out to disk.
Okay. So if I can I ask a second question?
Yeah, you can.
So you mentioned the ARM processor several times, which I think is very interesting to see that it works already on the Fujitsu Fugaku machine. Now, and in Europe there are some developments. So my question is actually the European ARM and the Fujitsu ARM, are these really the same things, or is that now getting somewhat separated and they just have the same name?
It is the same instruction set.
Okay.
Right. But, how many memory channels they put on, how they configure the chip, how many cores it will have, and so forth. This will be different. And there is nothing publicly available about the European processor yet, unfortunately, so you could compare it.
But is there a collaboration with Fujitsu, or
they collaborate? Yes.
Okay. Thank you.
Okay, so I think that it's time to move to. Thank you very much, Erwin. And I think that it's time to move to our second talk of the session, which is going to be given by Matthew Smith. So, yeah, you can share your screen.
Sure. Is the audio okay?
Yes, we can hear you.
Excellent. Good. And 1 second.
Yeah, we can see your screen now.
Excellent. Okay. Well, Thanks very much, and thank you for the opportunity to present today at the workshop. As you can see, I'm representing the Barcelona Supercomputing Center today. However, I only joined the center about 2 weeks ago. My background is in computational physics, particularly condensed matter theory and DFT, and also in HPC. So I'll be talking today mainly about work that I've undertaken prior to joining BSc, and that works at the University of Cambridge, and working on a particular DFT code there that I'll be talking about in detail. So I thought it would be remiss of me, despite the audience, to give a talk on density functional theory codes without at least a very brief introduction to DFT itself. DFT is, of course, popular for its acceptable accuracy and acceptable cost. At the heart of DFT is, in the formalism that I'm considering, is a set of n nonlinear eigenvalue equations, which, as I've written here, all of the symbols have their usual meanings. H is the Hamiltonian matrix, which is a function of rho, the density, and phi is an eigenstate of the Hamiltonian. I've labeled the eigenstates with B because I'm considering mainly the solid state context, and so B stands for bands. And clearly it's a self-consistent solution that's required. And the distinction that I'm making in the approach to DFT computationally is in two main categories: order n being linear scaling with the number of electrons in the system, and cubic scaling, which is what I'll be focused on today, and how we can meet the demands of exascale, or edge towards the demands of exascale, in cubic scaling DFT. So the code that I'm going to be talking about mainly is CASTEP, with which some of you may be familiar with. CASTEP is originally based in the UK, developed in the UK, and it uses a plane wave basis, as I said, and so is traditional cubic scaling DFT. It's scalable to thousands of cores, primarily through distributed memory parallelism via MPI, but also through OpenMP, and more recently OpenACC, which I'll talk about imminently, the move to that platform as well. And being a plane wave basis code, of course, the FFT is the primary means of leveraging the efficiency of the basis, moving between the native Fourier space and direct space to apply various matrix operators to the eigenstates, or the trial eigenstates, and essentially these can dominate the computational cost in one way or another. So the work that I've particularly focused on, and the recent developments that I'm going to focus on in the talk today, are to do with optimizing the parallelism of the FFTs in one way or another, and I'll focus on the details of how the parallelism is or isn't edging towards greater strong scaling for exascale machines. Just before I go any further, I just want to be clear on the dimensions of parallelism in a plane wave basis, or particularly in CASTEP. The main object is the eigenstates of the Hamiltonian. This is central to all the computation. And as you can see, the phi here has acquired an extra label from the B, which is B still is an eigenstate, but K stands for a K point, which is just a sample point in the solution space. The number of bands, the number of eigenstates ranges in Cas-Step from, say, orders of 100 for a small to medium-sized system to, say, 1,000 for a larger system. And we can parallelize over the bands, although there are limitations to that, mainly due to overlap integrals in matrix elements that can limit the scaling due to the comms that's required for orthogonalization of the eigenstates. The K points, on the other hand, offer the most opportunity for strong scaling because the equations over K are very loosely coupled. However, as the system size increases, the number of K points reduces to 1, and so it becomes a null, it becomes a moot point for parallelization. And so what I'm particularly interested in is the Fourier components, or the G vectors, as I'll be referring to them. And these offer the most scope for large process counts, and therefore strong scaling, or at least the opportunities for strong scaling. In Cas-Step, you'll typically get something of the order of 10 to the 4 for a small to medium size system, and then up to 1 million for something larger. So the 3D FFT grid over which we operate when it's memory distributed becomes, of course, involves free 1D FFTs and then 2 grid transposes, which are performed via all-to-all V in our case. And I'll be talking about the problems associated with that, the well-known problems associated with that in the forthcoming developments. So let's begin with the first of these, which is porting Cas-Step to GPUs in particular, but accelerators generally, to try and leverage the performance of heterogeneous computing. We currently offload 2 major bottlenecks to GPUs. One is FFTs, although not using memory distribution, G vectors, and the other is matrix multiplications, particularly in the application of the non-local pseudo-potential operator. Now, the FFTs are really only a bottleneck in small to medium-sized systems. At scale, the FFT kernels themselves are negligible. The matrix multiplication, on the other hand, can be a bottleneck regardless of the system size, although of course diagonalization is the major bottleneck in DFT codes. As yet, we haven't been able to offload that successfully, or efficiently, I should say, just simply due to the sizes of the matrix for diagonalization relative to the transfer costs. Although I think that is changing soon with the optimizations that we've made, and also the NVLink becoming more readily available, and so on and so forth. But anyway, as yet, these are the 2 major bottlenecks that we've looked at. And our port is an OpenACC port, which we use for the allocation and deallocation of device memory, and also transferring the data. And then we leverage the power of the libraries and so on, as well as optimizations ourselves in OpenACC. And one thing that one area that I've been particularly interested in is the acceleration of so-called hybrid exchange correlation functional calculations. These are an important class of calculations. They offer a greater degree of accuracy relative to other exchange correlation functionals for particular systems. And the reason that I've been particularly interested in them is, well, for my own research interests, but also because they provide an opportunity to showcase the capability of the CASTEP GPU port. The reason being that in a hybrid exchange correlation functional calculation, the runtime is almost entirely dominated by the FFT kernels themselves, regardless really of the system size, or at least to some extent, regardless of the system size. And the reason for this is that the FFT, the number of FFTs scales quadratically in the number of sample points and also the number of bands. So, so essentially, if you optimize the runtime of the FFT kernels, you optimize these kinds of calculations. With that in mind, what you can see on the in the figure here is a comparison of the speed up of CPU versus an initial GPU port versus a final refactored GPU for these particular kinds of calculations. And this is the time per SCF cycle, the SCF cycle being the main loop in DFT and CASTEP codes. As you can see, we get an impressive speed up, as we might expect. The CPU relative to the initial GPU port gave us around a factor of 10, and that's pretty much just by giving the by offloading the FFT kernels directly to the GPU, and the acceleration comes from there. Very, very limited other optimizations that we performed, but then refactoring the code again, looking at extending data locality and so on and so forth, we're able to get up to 16 or 17 times for these kinds of calculations. And looking at this from a slightly different point of view, the figure that on the right here is the refactored GPU port bandwidth, which, as you can see, is approaching 700 gigabytes or so for the kernels that we optimized, including the FFT library kernels, but also others, as I said, auxiliary kernels to those. And the maximum bandwidth that we measured on the system was around 800 gigabytes per second. So we're confident that we're approaching the optimum for this particular class of calculations here. Now, there's an important point to make, however, with this. These calculations were performed on the Ascent system. The CPU is 1 MPI process and 21 OpenMP threads. We're only using a single K point here, a single sample point, but we get this kind of speed up if we, similar anyway, by parallelizing over multiple K points, because as I said, the coupling between the sample points is very weak. Now, using 21 OpenMP threads in CASTEP is really perhaps not quite a fair use of the parallelism. It doesn't scale well with that number of OpenMP threads for one MPI process. But nevertheless, the reason we chose this was because it uses one full node of Ascent. So therefore, we can compare one full node with Ascent with the CPU and GPU combination, which is literally one MPI process attached to one GPU via the GPUs here at V100s with NVLink2. So as a proof of concept of targeting a particular set of calculations, which we're confident we can parallelize over in terms of K points and to some extent bands, but not G vector parallelism necessarily, and being able to offload a computational bottleneck to the GPU, we've achieved our goal. However, there are numerous challenges relating to this that I'll now talk about. So first of all, Fortran OpenACC CASTEP is a Fortran code, almost exclusively a Fortran code. And we chose the OpenACC platform because the platform is mature in terms of acceleration relative to, say, OpenMP. It's also an open standard relative to, say, CUDA or something of that nature. There's multiple compiler vendor support, which is an important feature in terms of people being able to actually use CASTEP. And as I think we demonstrated in the previous slide, we can achieve comparable performance to CUDA if we know what we're doing and we target the right kinds of calculations. I should point out here as well, for the semi-local and local exchange correlation functional calculations, we get something like a 2 times speed up relative to the CPU. So it's very significantly different from what we just looked at, but to be expected, I think, because of the difference in the kinds of bottlenecks that we're addressing with the accelerator. So the OpenACC platform has served us well in some respects, but perhaps not so well in others. There are limited feature sets in the OpenACC compilers for Fortran. I'm talking specifically about Fortran here. And just as an example, the NVIDIA HPC compiler, NV Fortran and so on, lacks support for device-only allocations. For those who are interested, the device resident clause actually aliases to create, so you end up with an allocation on the device irrespective of what you've actually put into the code. Now, the reason that I mention this isn't to complain about a particular compiler or anything of that nature, but rather to draw attention to the fact that what does it say about the future of Fortran accelerator compiler support if such a large player in the accelerator space as NVIDIA is not providing support for such an important part of the OpenACC standard. And you may say, well, it says that Fortran is dying or dead, and therefore we should move on from it. But the fact is, CASTEP is a leading electronic structure code, and it's written almost entirely in Fortran. The same can be said for say VASP. It certainly uses a lot of Fortran. The same can be said for ABINIT. The same can be said to some extent for Quantum Espresso. The same can be said for Siesta, which is a linear scaling DFT code, and so on and so on. And I know all of these are not using OpenACC for their acceleration, if they do have acceleration, but still, the point is that where does it take the future? I don't have an answer for this, but I'm hoping maybe it will provoke some discussion after the talk. One other thing to notice here, which will be relevant soon, is that there's no CUDA IPC equivalence as yet in OpenACC, certainly not one that's been implemented in Fortran readily. And this tends to bloat host-to-device transfers and can limit the system sizes that we deal with. And why this is particularly important is because, as I've said, G-vector parallelism is really vital to maximize the parallel scaling of CASTEP and plane wave DFT codes in general. So the problem that we're meeting in the development of that is that the CUDA-aware MPI efficiency is reduced by the overhead of the buffer preparation on the device. This is all about device data. We're not talking about host-to-device transfers at this point. And the problem here is that the number of non-vectorizable kernels grows in proportion to the size of the MPI communicator over which we're performing the all-to-all, the MPI collective. And the reason they're the fact that they're non-vectorizable means that they run particularly slowly, of course, on the device. And then on top of that, in a plane wave code where we have distributed memory, FFTs, then we're typically dealing with small numbers of data points being transferred from one process to the other in the communicator. And so we have low computational intensity of the kernels. So these two things just tend to undermine the efficiency of the CUDA-aware MPI. Of course, it's much worse without the CUDA-aware MPI, but still, it's not a panacea to these kinds of problems. Of course, if we had CUDA IPC equivalents in OpenACC, some of these problems could be avoided potentially, but there's no support for that, so we have to try and get around it in some other way, at least at the moment. And just one other thing to mention here, the performance that we saw in the previous slide for the FFT kernels really relies on the batching of the FFTs because, as I say, we're dealing typically with not, the data sets simply aren't large enough to saturate the device. And so we have to batch them up in order to get the computational intensity up to something that amortizes the data transfer. But the repackaging of these, when we come to G-vector parallelism, we have to repackage the data into contiguous buffers. So all we're doing really is adding more low intensity kernels and increasing the memory footprint. So these are significant challenges that we have, at least in our Fortran OpenACC port at the moment. There's active work to address these. They're not necessarily insoluble, but I'm highlighting them because they are issues that we need to address. Okay, I'll move on now to the second of the developments that I've looked at, which again is related to G-vector parallelism, but here I'm talking about only on the CPU side of things. This is independent of the GPU port. And I'm also not focused at all here on hybrid XC functional calculations. I'm talking entirely generally about CASTEP and its performance. As I mentioned earlier, we deal with typically relatively small data sizes being passed in the MPI collective. So if we scale using G-vector parallelism, we're typically in a latency bound regime, which is obviously for an MPI all-to-all collective going to lead to quadratic comms, and the comms limits the strong scaling of the code, which is just demonstrated in this slide here, where if you look at the bottom slide, you can see, or the bottom rectangle rather, you can see the comms. This is comms only from the all-to-all V in FFTs, and you can see that as a percentage of the total wall clock time. Even scaling from 64 to 1,000 cores here on a reasonably, I would say, a medium-sized system. We've got 270 atoms in this system. The comms is reaching 50% or so of the total runtime, and obviously nullifying any parallel scaling beyond that point, or sometime before that point, in fact. So this is what we've tried to address in our developments, and that's what I'm going to talk about now. So the solution to this is well known, really. What you do is, in principle at least, is just to take your effectively 1D chain of processes and map them to your FFT grid and some 2D logical process grid. The reason why this is efficient, of course, is because then in the all-to-all in the process grid, if you confine the all-to-all to the columns or rows of the process grid, then you're dealing with about root n processes. So when you get the quadratic scaling of the all-to-all, you actually end up with linear order in the number of processes, in the comms due to the processes. This is of course well known. It's established in other fields, but has been proposed numerous times over the years in plane wave DFT codes, but to the best of our knowledge has not been implemented, at least not at scale, in any widely used plane wave DFT code. And perhaps one of the reasons for this is because the use of the logical process grid has issues for the load balancing of the plane waves in the G-vector parallelism in a plane wave DFT code. And what I mean by that is that CASTEP uses a 2D domain decomposition, with this simple schematic of that here, of course, and the fine-grained load balancing is complicated by having a native a spherical native Fourier space, which is what you can see in the right-hand figure. And what we've got is the sphere here is where the eigenstates of the Hamiltonian are defined. But as I've written it here, this is in a real space or direct space representation, but their native space is in fact the Fourier space. So we have them in this compact format, but in order to compute the density, we do this in real space, and because the density goes as the magnitude squared of the eigenstates, we have to expand into a cube, the volume of which is 16 times greater than the sphere in which we started. Now, clearly, if you superimpose the 2D domain decomposition onto this cube, or indeed onto the sphere, I should say, not the cube, you're going to end up with a load balancing issue. And there are numerous ways in which this has been addressed over the years, but there's not really been a robust, provably optimal way that this is being addressed, and certainly not in conjunction with a 2D logical process grid implementation. So what we've done is to develop an algorithm that does indeed optimize the load balance and provide the optimal comms via the 2D logical process grid. What you can see in the top two slides here is the default unoptimized, if you will, distribution in CASTEP. This is the G-vector sphere, so this is a Fourier space. Just a toy example of 6 processes. Here's the load balancing, but this is what it would look like in CASTEP. And what you can see at the bottom is the optimized G-vector sphere distribution and the accompanying load balancing here. And the important point to take here really is that in the top we have a load balance of a factor of 2 between the least and the greatest, whereas in the bottom side we have a factor of about 1.4. And more importantly, the load balancing in the top is the default load balancing scheme in CASTEP, whereas the one in the bottom is our new algorithm, but this is provably optimal and it's robust. So effectively, we have indeed optimized the load balance. We're confident in saying that, and then we can implement the 2D logical process grid to then address the comms as well. So what does this look like in practice? As I said, this is just as an illustrative example, but in practice it looks something like this. So here, the system that we run on, the HPC resource system that we run on, is Archer 2, which is a UK tier 1 system. It only has CPU support only. It's not a heterogeneous system. And so on the bottom axis, you can see the cores there. And then on the vertical axis, it's the time for 10 SF cycles. So the time for 10 main loops of the code. And the figure at the moment is showing just CASTEP, pure MPI. And you can see for this moderately sized system in CASTEP, we're bottoming out at around 512 processes, after which there's no point in further parallelism. If we introduce some OpenMP threading, 4 threads per process to this, we can extend the parallelism to around 1,000 processes. One of the reasons for this is that we are only having 1 in 4 of the processes involved in the all-to-all, so we're significantly reducing the all-to-all comms bottleneck there, also accelerating other parts of the code as well through the OpenMP support. But still, we're only getting to this 1,000 core limit here. And if we introduce the grid, then okay, this is pure MPI, no threading, and this is without actually implementing the sub-communicator comms. This is just effectively the load balancing that you're seeing, and you can see immediately that we extended the scalability just of the pure MPI to around 1,000 cores, after which there's a steep gradient there as it falls off. But if we introduce the sub-communicator as well for the pure MPI, now we're extending it to around 2,000 cores. So if you compare the sort of pink line here to the dashed line that we started with, we've gone from 512 to 2,000 or so. And then if we go one step further and now introduce the, so we now have the full complement, if you like, of the process grid working with the sub-communicators and the load balancing with the threading of OpenMP as well, we can get to around 4,000 cores, after which we actually run out of data with this particular example, so we can't extend the scaling any more than that. But as you can see, there's considerable room here for optimism in how we can progress with this. And there are several optimizations we've yet to do. This is only a prototype implementation, really, of the algorithm that we've developed. Having said all of that, there are significant challenges still, of course. What I've just talked about is extending the strong scaling of the plane wave DFT code for a moderately sized system to around 4,000 cores. Well, that's not going to get us to Exascale on its own, quite clearly. Although it's positive, it's not a solution. So very briefly, I'll just pose a few questions, really. Can we redesign and optimize existing algorithms? One example of this that relates to the GPU port that we were looking at earlier is the adaptively compressed exchange formalism. Some of you may be familiar with this. This is particularly GPU friendly, and we've implemented this in CASTEP and it works well, but it really requires CUDA IPC equivalence in order to optimize it. Also, is there a possibility of introducing new dimensions of parallelism? One area that's under active research in CASTEP is to implement shift invert methods for solving SCS cycles. I'll say no more about this because my expertise in this area is very limited, but still, it is an area of active research. Also, I think importantly here for the CASTEP strategy is similar to the GROMAC strategy that was mentioned in Erwin's talk, where we're talking about, can we achieve exascale in the code itself for our core computation? No, perhaps we can't, but we can adapt our workflows and so on, and therefore move to more cores that way. And finally, the question still remains, should we just rethink from scratch as is sometimes said about plane wave DFT. Do we need to rethink the algorithms from scratch? Where is the future of all of this going? Can we achieve what we hope to achieve, or do we need to be take a longer look at ourselves and say, well, perhaps this can only work at up to some particular scale, and we won't get to the exascale with this form of DFT. Well, anyway, these are questions which I hope will at least provoke some discussion or some thought for after the talk. What I'd like to do finally is just say thank you to Dr. Phil Hasney, who I think is in the audience today. He's been my PhD supervisor. He's a CASTET development, part of the CASTET development group, and also at the University of York. He's been, of course, instrumental in the work that you've seen here. And also just thank you to all of you. That brings me to the end.
Thank you very much. So I've seen that there's already a question in the chat by Erwin, who's asking if you tried the CUDA Fortran instead of OpenACC.
Yes. 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 I think one of the issues there is you're tying yourself, of course, into one particular vendor. Also, for that itself is not isn't that fully featured relative to CUDA C, and of course the maintainability of the code also becomes an issue. You've got your CUDA being developed alongside your CPU Fortran, and so there are issues with that I think can lead to problems there.
If I may ask a question also, so I mean it's a bit in the line of the one that I asked to Erwin, and it's related to your last question. I mean, and I think I'm convinced about that, we go to large scale computing and don't distinguish high throughput and high performance computing.
Yeah.
And I mean, okay, is it really useful to invest so much in changing the code to adapt to something when in the end to answer a given question, because we have to answer a given question and not a given simulation, we need to do many simulation, which can be in a sense high throughput. And so maybe it's worth investing in things that, as Mathieu was pointing, require that once maybe a job is finished, it's reassigned a new job. Once a job is finished, the nodes are reassigned to another job. That might be a bit more, you know, I wouldn't say useful, but more in terms of invested time to reward more important.
Yeah, absolutely. I think this does relate back to what Owen highlighted in the GROMACS strategy, where we're looking at trying to optimize the core computation within the code, but also how can we then exploit for different kinds of calculations, how can we exploit massive parallelism by as you say, perhaps a good example here is phonon calculations, where you can distribute the work over different dimensions of the calculations and so forth. And then also in active development in CASTET is automation of the parallel strategy and how that should be used in relation to a given hardware set at runtime. So all of this is working towards that kind of goal. But I think it's vital to actually get the optimal performance from your core calculations in the first place, and to say, well, that is now effectively a solved problem. So what else can we do?
Yeah, because I mean, I didn't mind. So sorry, I went and then I'll leave you ask your question. I mean, I didn't mind something which, in the end, I mean, you're going to do a number of calculation from which maybe you're going to do some machine learning, and your final answer depends on a number of calculation, which can are in some way independent from one another. Well, not in some way, they are independent from one another, though they are connected to the fact that they are helping you to answer a question, you know, and this is the maybe the idea of the workflow.
Yeah, yeah, I agree.
Okay. Okay, Owen.
Yeah, I just have a comment that actually Matthew just said as well. Yes, we need to look at these ensembles and how to run them as efficiently as possible, but we must not forget the single simulation efficiency over that.
Of course,
This is still core, and because the resources are still scarce, right? And we have to share them with many others. You need to be as efficient as possible, and then you can start dealing with the efficiency of the ensembles.
Sure. But there's
one
no
thought
way.
again there also is, I think this will be a place where a lot of AI technology can have a role.
Yeah, because there's no way you can beat independent jobs. Huh? So if you have a number of independent jobs that are needed to then do some kind of machine learning,
yeah.
I mean, there's no way you can go faster than independent, basically. Yeah. Other questions? Okay, so if not, we're about at the time where we can stop for half an hour and we reconvene for the last talk by FAIR-DI. Thank you all very much.
So Gianmarco, where are all the other people, the 12 other people who were there yesterday? Actually, I think you are muted.
Actually, I cannot unmute. It's okay. Can you hear me now?
Yes, fine.
Okay. Yeah, I cannot unmute myself. We have a microphone here. So yeah, some people went back home, and the students they did, you know, since we decided to go to, we knew that there were going to be less people in the audience, and so they did some well, they are online as well.
Okay.
Some of them,
yeah.
So Tom had to leave after lunch. Elias left yesterday. Fabien the same. So yeah.
Okay, good.
It was interesting to have this hybrid format. I think it went quite well in that sense, and so we're building experience on that. Yeah.
No, I think actually it went pretty well. I mean, I would say really for people on the screen at home, which is actually at home is always difficult because you cannot hide, right? You are also available for something else, so that's a bad thing. And then a full day is really quite a lot. But I think under these conditions, I think we had actually very good speakers. I think it was really nice.
Yeah.
And there's one more coming.
Indeed. So it's time to announce indeed our last speaker. So that's Bert. Yeah, that's Bert de Jong from the Lawrence Berkeley Lab. So Bert, the floor is yours. You can share your screen. I don't know if you're speaking, but at this stage.
No, I was quiet.
Okay. So, okay, we can hear you.
Make sure I got my slides up.
Yeah, sure. Just wanted to make sure that we could hear you.
Yes. Now, Matthias, I agree. It's a challenge to work in a hybrid mode. And especially if you want to really have collaborations across time zones, it becomes a very hard and very challenging problem. But we do the best we can in these tough times. I was asked to talk a little bit about Exascale, and I took the liberty after looking at the agenda to broaden myself a little bit. And so my talk will be on Exascale computational chemistry, and also a little bit on the chemistry genome, because I think those two are not uncoupled at all. Oops, keyboard's fun. Okay, so just to give you a little bit of context on the way I think about these problems in general and how I approach my research. So I see computational chemistry really as a tool to help us go from understanding to control. All we're after when it comes to computational chemistry, but also computational materials, is an experimental side too, is to get fundamental understanding that allows us to develop new materials, new processes that allow society to move ahead. So a couple of examples of that are very simple. Let's say we want to have more hydrogen production. How can we do a more efficient photoinduced catalysis of water to generate hydrogen for an hydrogen economy and a new energy source? Of course, when it comes to the world of quantum computing, if people have been keeping up with that, one of the hot cases that they want to sell there is the nitrogenase enzyme, where we try to understand simply how the FOMOCO system works in generating fertilizer effectively out of ammonia and out of nitrogen and hydrogen, without the large energy footprint that we have. I still think that even though they claim that this is going to be an important one for quantum computing as a kind of a stake in the ground, I think classically people are getting more and more closer to trying to actually model these kind of systems on the chemistry side. So, as I said at the beginning already, really discovery and then being able to go from fundamentals to control really requires insights and solution from a very interdisciplinary set of research. And I think these FAIR data environments are critical there. So our part really is simulation there. It's right, it's yellow, the yellow box is simulation, but we really need to bring together simulation, experiment, theory. And now I would say the fourth pillar is really becoming machine learning or AI. And actually, machine learning AI cannot go without the other three. It needs the data that comes from those kind of components. But it allows us to get a lot of insights that we were not able to easily get out of the other pieces. So if you look at what my group and my environment has been doing a lot, it's really we're looking to driving towards virtual experiments for understanding and discovery. And what I mean by virtual experiments, I would like to be able to do what an experimentalist can do at the same level of accuracy or more accurate, but have more insights because I have different ways of looking at the information, looking at the wave function, or even be able to probe areas that are not easily accessible by the experimental community. So my toolbox, and this is how I look at these kind of things, my toolbox is exascale quantum chemistry, quantum computing. I could talk hours about that too, and machine learning and AI. And it's those three tools, and that's what they really are, that help us really do the science we want to do on a computational framework to discover new materials, molecular systems, drugs, etc. So let me dive a little bit into the exascale for chemistry and materials. Why do we want to have codes that scale at the exascale? Well, simply we need the exascale codes to tackle the science problems at a scale and accuracy that are not accessible otherwise. Chemistry and also material science have always been constrained by the computational resources. We are early adopters of computing and HPC, but we always have been constrained by the resources that are available. Another advantage of being able to run at exascale is that you can provide data and benchmarks that allow us to, oh, there's a typo there, that allow us to give us experimental understanding at the same accuracy as the experiments, but also provide us the essential reference points for machine learning. I know I was listening a little bit at the discussion of the previous talk, so I added this note at the end. So high throughput does not need an exascale code, right? So there is definitely two different classes of codes that can run on exascale platforms. We can take our current codes and run them on high performance platforms as much as we want, as long as we can use a GPU or something like that to a reasonable efficiency. We can just do high throughput of small calculations. But when it comes to real large scale problems that you cannot solve on a smaller platform in a reasonable amount of time, you need to have scalable codes. So within the US, where the national labs took an approach to pursue exascale development through what's called the Exascale Computing Project. This by now is, I think, between $1 and $2 billion that is going to be spent on this, where the Exascale Computing Project is really considered a construction project to build the next generation exascale platforms. So the US will be building two, one at Oak Ridge National Lab and one at Argonne National Lab. They are at, I don't even know, I think they're at 250, so they're at a quarter of an exaflop right now at Oak Ridge. So this project is very interesting in the sense that what they did is they integrated application development. So they are looking at all the different domain sciences. Chemistry is one of them, but looked also at all the technologies that are needed to make these applications run on hardware. And of course, hardware has been evolving rapidly again over the last couple of years and is still evolving, because at this point, some of the exascale platforms, it's still not clear what the hardware will finally look like. So they really need to have a program that integrates horizontally and vertically all the hardware technologies, the basic software stacks, and the application development. And this is a massive undertaking that we have been a part of. So most of the people, if they know my background, know that I am a long-term NWChem developer. I led that group for a while. So under the Exascale program, NWChem is going to go from NWChem to NWChem EX. We're not very inventive when it comes to a name. But one thing that is important to know is that we're not adapting NWChem to the Exascale. We actually have chosen to start from scratch and completely rewrite and redesign NWChem. So it's not, here's a code, let's just modify it. Our choice is to really go after cutting edge programming languages and models. From what we've learned from 20 years already, we are actually choosing new approaches. So one of the big things will be that NWChem EX will be fully the latest and greatest C++, for example. We are fully exploiting advances in computer hardware performance. So this ECP project is very conducive for that. We work with the lower level software stack developers, the solver people, and also with the hardware vendors to make sure that we are coding towards platforms that make sense and use the technology in a way that is the best way it can be. Use the best in application performance engineering. So we have a lot of computer scientists involved in our project. And we're also implementing and tuning the latest computational chemistry methods. So NWChem used to be a code that is based on dense algebra. So all the methods were dense, none of them were sparse. One of the key things is that we're going to focus purely on sparse methods and reduce scaling as we can. And also from a design point of view, we want to have a maximum flexibility in method composition, and hopefully that will come across. In addition, nice part, we can use actually AI to accelerate parts of our simulations. Think, for example, initial guesses, think of iterative processes where we can use the information of previous iterations in a different way, in a machine learning way, to accelerate the simulations. Geometry optimizations use knowledge about the chemistry systems for initial guesses, etc. So again, why did we not go with NWChem and just modify it? Because over 20 years, NWChem scaled pretty well when supercomputers grew. We've been able to use from megaflops to petaflops without too much trouble. However, when Moore's law came around and all of a sudden they couldn't really scale the conventional way of scaling and growing architectures, our architecture kind of showed the aging, and we ran into issues that we had to redo a lot of code with GPU, redo a lot of code with multi-core, and still we would be running in a lot of concurrency bottlenecks. Now, GPUs, multi-cores is nice. The new exascale architectures are even more complex. Now we have to do concurrency across multiple GPUs. GPU technologies are not going to be the things that we have been seeing so far. New programming languages are needed and used to actually access it. So CUDA is great for NVIDIA, but for example, on other platforms, we have to use programming languages like SQL to really get performance. This is an Intel product. So there were just significant limitations to the extensibility of NWChem. One of the big things is that if we wanted to add new methods, it was so monolithic. It was just hard to add anything new without breaking something else. Again, I said already, we do everything in dense. So actually sparsification of our algorithms was a challenge. Everything was very coarse grained. And data was not on the forefront in a lot of ways on how we actually dealt with our computation. While if you look at the next generation platforms, it's actually data and the data movement that is driving more of a performance than the compute cycles themselves. What's interesting also is if you look back at when NWChem was designed and developed, the type of scientific questions we were probing at that point were rather different from what we're trying to do now. So these are actually our target kind of reasons why we went to NWChem EX is we want to get to problems that are a lot more of scale. So can we actually start modeling ion transport and help in the production and improve the production of biomass? Can we design better proteins, right? Similar to that, can we develop more efficient catalytic processes to then take that biomass and form biofuels? So you see there is a lot more energy bio, a more heterogeneous type of problems that we're going to tackle compared to what NWChem wanted to do, which was big, smaller molecules, high accuracy. So one of the things that we are kind of trying to adopt is a hierarchical approach of computing, so embedding and those kind of technologies, and then being able to get accurate analyses of forces for these large-scale realistic models. So for example, our target is that we will be able to do high accuracy Hamiltonians, couple cluster and beyond, at thousands of atoms in a reasonable amount of time. And then that should be embedded in an environment of hundreds of thousands of atoms. And we're not talking about doing hundreds of thousands of atoms then at the molecular mechanics type of level, but more at the DFT level of time. In reality, these systems are not static. They're all dynamic, right? So we need to be able to do this very rapidly too, so that we can start thinking about potentially some short-term and short-time dynamics. So this is another reason to really pursue reduced order methods that are faster and more efficient for dynamics simulations. So NWChem EX, as it's targeting the exascale, will be a combination of not just using the hardware, which is our horizontal axis, but also reducing the scaling complexity. For example, what we show here is on the vertical axis is think of couple cluster, where in the dense form it's an n to the 7th, while if we do something that DLP&O or better, we can go to something that is sparse or an n order n to the 4th. We believe that to get the performance and get the capabilities that we need for the next generation of computational chemistry science, we need to do both. It's interesting if you really think about it. If I take a dense method and scale it from a teraflop to an exaflop, I only can tackle a problem that is 7 times larger. That doesn't really help us, given the problems that we want to run right now are way bigger than a 7x. So we need to do both. There is a challenge with that, because the more sparse you make it, the less compute you have, the more data movement you have to do. So we also made ourselves the problem a lot harder scaling these kinds of codes. So just a little side note here is that ECP is truly a construction project. They run it as if it's building a building. So we actually have real targets to meet. So our target that we are going to do on a exascale machine is ubiquitin, which is 1,231 atoms, 39,000 basis functions. So that's a pretty tall order to get there. So right now, when we do we don't have an exascale machine. And if we have access to exascale-like machines, we don't have a lot of hours to go and run our tests. Currently, we're running something that's a little smaller, which is the DGRTL. So that's a fragment of that. It's about 80 atoms. But what's interesting is, again, we have a target. We have what's called a figure of merit of 50. Now, that is not saying, here's a problem, run it 50 times faster. It's a little bit more complicated, but roughly is what I can run on a petascale machine. Can I get at least a 50x improvement over that on a similar size of problem on a similar size machine. So I mentioned already, there is a lot of need to make sure that you take advantage of the latest technologies. So one of the things that got dropped pretty late in the game when it came to NWChem is that we focus more on the parallel scaling and not as much on the single node scaling. We really are conscious this time to make sure that we can perform on the smallest single node scale. And in this case, a single node is actually already 4 GPUs, and actually that we can actually get performance out of this. So the fragment that I showed on the previous slide, we've been running these on the latest hardware. So NVIDIA is one of the hardware platforms that is going to be in the Exascale realm potentially, but the Oak Ridge machine will be all based on AMD, which is a very different technology compared to NVIDIA. But as you can see in the numbers here, we can actually do pretty well in getting performance out of the AMDs compared to the NVIDIA V100s that are out there right now on the Summit platform. What's interesting though is that what we did here is, this is a triples kernel from CCSD. We took a CUDA code and it was ported using Hippify. So their Hippify model is what AMD wants to program under Hipster. What's interesting, we were able to use a simple tool and get still performance. There is, of course, a lot more performance to be gained if we do a application-specific hand-coded version of Hipster on an AMD platform. But the nice part is that we can get already good performance out of a platform simply by taking a CUDA code and transferring it. We're working now on other aspects of the code to do the same thing. Here's an example, for example, when it comes to DFT. And so we are not just doing couple cluster, we're also doing DFT. So we're able to get pretty good performance out of these types of platforms with accelerating GPUs. So the Ubiquitin is the big 39,000. Well, it was not run at the 39,000 basis function, but it's about 11,000 basis functions. We were able to get within a couple of nodes, a pretty good 30x speed up going from the old NWChem to NWChem EX, going from CPU to GPU. So that gives us confidence that even the more expensive models, which is still dense, can give us already a good speed up on the next generation platforms. So underneath, we're going to actually use libxc, which is well known. We've been working on a port to CUDA for the libxc code. So the link is actually there. That should be available to others. And within FAIR, I think FAIR is not just about data, but also about code. So we are sharing everything we can with the community. So look a little further. So here's an example where we actually starting to take both the sparse and the scalability at the same time. So we are using a Koleski version of CCSD. So we are actually reducing complexity with the Koleski and are able to get almost 120 times speed up from a implementation that would be running on a platform like Titan, which is the previous our Oak Ridge system with NWChem, compared to now the NWChem EX on Summit. So we are getting the performance that we need. So to some extent, here the form would be about 50x. So we're actually achieving that by combining both the hardware advances and the methodological advances. And it still scales. These are not large problems. So you talk about the small fragment of ubiquitin at ArcCC PVDZ, it's 1200 basis functions, and we can scale those to 250 nodes. What we're talking about is 1500 voltas in this case that we are running on, because the IBM Power 9s are nothing than data movement engines at this point. We are running purely on the NVIDIA Voltas in this case. So it's a lot of cycles and a lot of performance that is provided to us, and we can still scale for these relatively small systems. If you go to triples, everybody knows that triples, relatively speaking, is a little easier to do. We actually have been running that on 4,600 nodes of Summit, which is getting close. Sorry, 4,600 cores on Summit, which is about 220 nodes. It's about 20%, 10% of the system, and we can actually get good performance out of. Sorry, I need to reread this. So we ran it on a smaller scale of the system, where we get about a 68 factor speed up. We can project and estimate where we would be at a whole system. And we believe we can actually get the performance of a 50x at least speed up of the triples on a platform like Summit. We can also show that it does scale. So this gives us confidence that this is going to happen. So we actually can do a linear strong scaling of this simulation up to 2,000 nodes, which is about half of the Summit system that's there. The superlinear scaling that seems to be there seems to be driven by cache effects and how the memory can be laid out in memory. The data can be laid out in memory. So this is an important challenge to deal with. Okay, so I'll give you a little bit of an insight of what NWChemEX's first implementation will look like. It will have reduced order implementation, so localized Hartree-Fock and DFT. We'll be using numerical approximate kernels to accelerate the Hartree-Fock and DFT. But our main piece of code will be DLP&O based MP2 and couple cluster. We will also be releasing it with a PlaneWave code that has been rewritten. And so we can will be doing materials. Our goal is to really be able to do embedding between the PlaneWave codes and the reduced order implementations that are Gaussian based. So we will have energy gradients and embedding, and we have been putting a lot of effort in developing reduced order solvers for efficiency. You can just imagine going to these larger problems. We get a lot more issues when it comes to the solvers, and there's a lot of work that's being put on to make sure that that performs. We'll support all DOE machines, but if it supports all those big GPU machines, it will support anybody's platform that has GPUs in it. Our focus is going to be those technologies, although it will run efficiently on CPUs too. And it will be released under an Apache 2.0 license. An interesting aspect of this is that a lot of codes have been doing this now, but NWChemEX's front end will be Python. We're working really hard to find a way to actually run parallel through a Python interface. Of course, there is MPI for Py, but that needs to be able to move the key pieces of information down into the C++ code that is NWChemEX. So we are using a slightly different way than a lot of other people have been doing. Instead of using the using the standard approaches, we're actually using a product that comes out of out of LBL, out of the high energy physics world, and that's called CPPYY. That can actually generate Python bindings out of C++ header files without you having to write them. So we just identify the header files that should be exposed, and CPPYY will automatically generate the Python bindings instead of PyBind 11, which is a lot of effort. So we can do this pretty much automated. So we end up with very few CMake lines to actually generate the little inits that are needed for Python. This Python front end, of course, is one reason to do this is because it's easier to interface this then with machine learning in the long run. And this is something that we have been working on also. And I'm switching a little bit now into data science and machine learning efforts that we have been looking at. So this is a collaboration really between Marcus Hanwell, who was at a company first, but now at Brookhaven National Lab, together with Johannes Nachman, who has been developing machine learning approaches, and me, where we are really looking at how we can develop an open chemistry environment. In this case, we were looking actually doing this on Jupyter notebooks. Again, so can we in the long run run Jupyter notebooks and then run parallel computational chemistry codes within that framework? That would be what we want to do. So the approach that we've been taking here is actually to have not just a data platform, we also have a web platform, and our interfaces with a lot of codes is going to be through Docker. So we have implementations where NWChem and NWChemEx actually runs in through Docker and has RESTful APIs towards the notebooks, so we can run actually those different codes in parallel. So the Jupyter Notebook then allows you to go and combine with things like binders so that we can actually start sharing the data. And one of the critical things for us was to look at how we can actually integrate computational experimental data into this open chemistry framework. Again, I mentioned already in the beginning, experimental and computational results together will be essential. So our goal is really to have a platform where we can take these different types of data and then integrate them and provide a visual or a method to the end user to manipulate, process, analyze, or learn from the data. So for example, this is an example of ChemML, which is Johannes Nachman's code, where we can just run this within the open chemistry Jupyter notebook. All data, we have a complete infrastructure that allows all that data to be online and available within the open chemistry framework. But I would say we also build a connection to another effort, which is called the Molecular Software Science and Software Institute, which is an NSF effort here at in the US, where they actually have developed what's called QC Archive, which is also an archive infrastructure or a database infrastructure to compile and store and share computational chemistry, quantum chemistry data. So for those that are interested, I did want to point this out simply because one of the things that we've been involved with is their quantum chemistry schema. So they have been very active in trying to define a schema that allows us to have a kind of unified way of storing computational chemistry data. We're actually going to take within the NWChemEx this schema and provide output, data output within this schema so that it can be more easily and readily shared. So finally, okay, we have now computational data. What are we going to do with this? Well, one of the things is really, for me, a driver is to do discovery of the chemistry genome. This is kind of a plaquette of how I look at computational chemistry the chemistry genome. And that is really that we're after an end-to-end machine learning environment where it's not, here's a 3D structure, give me physical properties. That is very well understood and controlled, I would say, these days. My interest is really actually the reverse. Here's a set of physical properties and parameters. How can you tell me with AI or machine learning what kind of materials might be relevant to study or what materials might be relevant to be made and explored in either an academic or an industrial setting? The challenge is when it comes to then generating molecules, of course, is how do you encode those 3D structures? One of the things that we very quickly came to think about is, you know, materials, chemical entities, they're all discrete. This is one of the things that machine learning generally is not the best at. They like to have things that are contiguous. So we have to really develop machine learning models that allow us to deal with discreteness. And also features is a big challenge, right? What are the features that are going to be important? Should we tell machine learning models up front what features are important, or should we actually have machine learning models learn the important features? How big do data sets need to be? There is some machine learning models that they need millions and millions of data points. Well, there is also machine learning models that can do things a lot more efficiently. So we've been taking some other approaches. So I'll skip this, but definitely we are looking at the reliability of 3D encoding in a way that we can actually do generative 3D encoding. So anywhere in a latent space, can we actually find a reliable structure? What's interesting is we have been looking at a couple of different aspects. One of the aspects is looking at symmetry and hierarchy. This was actually work that was done by an Alvarez postdoc that I had, Tess Smith, who is now an assistant professor at MIT, where she actually looked at using symmetry information directly in encoding machine learning models. So her big contribution to this field is tensor field networks that allow them to get rotation and translation equivariant neural networks. And there is actually some applications that have been done in computational chemistry where they can show that they can use this to actually rotate even complete Fock matrices, for example, within this symmetry framework. The other effort that we have been doing is using different kind of machine learning methods that should be able to use less data to actually learn. So we have been focusing some of our efforts. So there's Yuang Tang is another Alvarez postdoc who is now a staff member at LBL. And I have been developing something that's called the marginalized graph kernel, which we use together with regression approaches. I won't go into the details because that is a long story on its own. But I can tell you that we can get extremely good results for multiple data sets. QM7 was a small data set, but the reality is if you go and look at the results, we can actually get results that are within a kcal per mole accuracy or even better using graph kernels and then Gaussian process regression methods. But the nice part is we could do that on 2,000 structures or 2,000 data points only. And one of the things that we have been exploiting here is also things like active learning, for example. What's nice about Gaussian process regression and marginalized graph kernels is that it actually allows you to get some information about the accuracy of the predictions. And it allows us to actually do outlier detection. And we're actually using this now in other ways where we integrate experimental data and kind of find data that is outside of the norm. And that allows us to either find data that is bad or actually find data that might be interesting because we didn't see that simply from the numbers that we saw in the first place. So this piece of code is actually available in GraphDot. So it can actually be downloaded by PyPy. It's a very efficient machine learning approach that can run on GPUs. It actually requires a GPU to run efficiently. But we've been able to get really accurate results of that. And we've been using this to now go and take the next step, and that is to look at ways to do inverse design. So for example, can we do smart searches? So one of the approaches we've been taking is we've been looking at AlphaGo, and we are pursuing a very similar Monte Carlo tree search approach that underlies things like AlphaGo and AlphaFold. The nice part is your code is not very complicated when you do something like Monte Carlo tree search, But the hard part is actually this expansion part, or the modification part, is how do you do this in a very efficient way when it comes to chemistry. So what we did is we actually developed something we call a context-based molecular graph rewriter that actually uses knowledge about molecules and the neighborhood of atoms. It knows, it has learned a little bit about chemistry in the sense that it knows that certain combinations of atoms in a row are more important than others. And we use that kind of knowledge to write new molecules. One of the things that we definitely take advantage of is something that Asper Guzik and his co-workers developed, and that is selfies. If you go and do smiles, for example, you cannot just simply make modifications without creating invalid molecules. Selfies really allows you to nearly guarantee that your changes lead to a valid molecule. So what we've been doing is we actually have been using this with the Clean Energy Project database, because one of the things that we want to do as a demonstration case is that we can actually learn band gaps for solar cells. So we use the marginalized graph kernel from GraphDot, and then, as I said, the underlying root is smiles based, but we have some dogs here that are not being nice. But one of the things we're looking at is actually combining smiles and selfies with the Lilleveld 3D structure predictor, because we know we can actually do 3D prediction in GraphDot and the marginalized graph kernel very accurately. So if we can take a selfies or a smile and convert it back to a 3D, we can increase kind of the predictability of our models. Okay, that one should have gone, that slide. Anyway, so we've been able to do that actually and demonstrate that these things work. We kind of had some initial molecules and tried to see how it would translate that. All we give it is a band gap. And interestingly, it finds sometimes molecules that we did not anticipate, and that is a good thing. They're all valid molecules. For example, when we were looking to go from pentane to isopentane, which is just a modification of the chain to a side chain, turns out it found actually a 4-ring structure that is just as close as isopentane. The uncertainty here, we cannot get exactly the band gap because our predictor has about a 0.1-ish error. So the band gap of 3.27, which is the last row in this graph, is pretty accurate. And then all of this is then combined in a broader package that we've been developing called ML for Chem, simply because we needed a framework to allow us to easily run these kinds of simulations, store the data, and be able to do machine learning it and allow us to have something that is reproducible. So also this package is available right now. It has a lot of different functionalities, but it's accessible on PIP. Okay, I'm almost on my time, so let me summarize. Exascale computational chemistry with MW-ChemEx, it will be accessible soon. It should be, the first release should be later this year. FAIR data, I'm kind of sprinkled that term throughout the talk a little bit. It's essential, and we've been developing various tools that are available, but also provide data in ways that it's accessible, findable, and reusable. Especially with the Jupyter notebooks, the reusable part is kind of the key infrastructure that we are after. So I discussed a little bit of the research we're doing when it comes to the chemistry genome and the molecular discovery. And as a closing thought, as I mentioned already, that there's a lot of different pieces that have to come together. When it comes to the development of ML or AI methods, especially things like inverse design with broad applicability, it really will require a lot of different data sources. And I know the workshop so far has been talking not just about simulation, but also experimental data. I would say another open field that people are starting to explore is natural language processing of literature, because there is also an enormous amount of knowledge out there in the literature that we should take advantage of. Can we integrate all these three pieces of information, simulation, experiment, and literature, to really accelerate knowledge discovery when it comes to scientific discovery? So finally, acknowledgements. So the Exascale computing project has provided a large amount of funding to make sure NWChem-EX can happen. And the machine learning and data science aspects are done through the lab's LDRD, internal funding, and SBIR funding. And that's all I was going to talk about. I thank you for your attention and staying till the end. I know it's a Friday late afternoon, and I appreciate your attention.
Thank you very much for this very nice talk and impressive work. I don't see question yet, so maybe I will start with one. So, I mean, this Exascale, NWChem-EX effort seems, a huge piece of work. And so I was wondering how many man months kind of have been involved in such a
Oh, that's a good question. I can give you a little bit of the size of the NWChem-EX project. So it involves 4 national labs, about 4 or 5 people per national lab, and then there's a couple of universities. And that involves staff and a lot of postdocs. Yeah, it's about a 25-ish people effort for the last, let's see, this is probably year 3, and we still have a couple of years to go.
Good, impressive. I think Matthias was first, and then Volker.
Yeah, so very nice talk, thank you. So on the NWChem developments, you said actually you don't really modify the code, but you rewrite it from scratch, which I understand to some extent. And I just wanted to ask you, what were the most important new concepts which you have used? I mean, one thing could be being more modular to some extent, but so what was really the key ideas in this rewriting?
So I think the key ideas more were on the side of what should we not do, right? So if you look at NWChem, when it was designed with homogeneous nodes in mind, a very flat memory structure, and dense algebra. So dense algebra is not what we are going to do. Everything is sparse. So data movement, it becomes a very different ballgame. Memory management becomes a different ballgame. And so it really came down to being more flexible in where you move your data and where you do your compute. So instead of having a monolithic data layout up front, we actually take a more step back and actually on the fly decide where compute and where data needs to be. So we actually are having a runtime underneath that is on the fly, given the problem size and what needs to be done, where the data should be. It decides how to distribute it and lay it out on the hardware, with options for work stealing and data movement on the fly too, because nodes might die, for example. Okay. Yeah, and the other thing is, in the sense of modular, we had a very NWChem, when you were installing it, it's a monolithic piece of code. What we've been doing now is actually building blocks that allow us to, that allow users to actually take pieces of the code and reuse. But also we're building a infrastructure such that it's almost like a plug and play type infrastructure, where we can easily take a new solver and move it into that. Oh, you have a better way of doing the exchange correlation. Well, we'll just move it in. That's how easy it should be. And the scary part is that's the original intent that NWChem had, but we were constrained at that point in time with 20 years ago with the programming languages that we had. We could not really, C++ was really early on, object-oriented. We tried to do that, but doing object-oriented in Fortran didn't work. Now we have a lot more flexibility with the really modern C++, C++, 1920, that we are pursuing, where we have a lot more flexibility on how we move and integrate data and how we combine pieces of code together. And that also allowed us to be more flexible when it comes to Python, which in reality is most of our end users is going to be people that know very well how to deal with Python and don't like to go and back and put input files together. So we really hope that this makes it a more user-friendly environment too. The nice part of the way we actually tied Python and C++ together is we already found out very rapidly that we can just write code in Python and literally have the C++ code use it, or we are just using parts of the C++ code that we get. Let's say we generate a FAC matrix from one thing and do something different, a different solver in Python, and kind of integrate that in a way more flexible development environment too.
Okay.
Volker?
Sorry, me. I have a related question, but well, more of an opinion question. You mentioned all the tools, right? But they work on exascale hardware. We know that even with the present hardware stacks and different software stacks, right, I think we have all sorts of problems in terms of having functional software stacks on top of the hardware that we're given. Now we have 3 different, or maybe 4 hardware stacks that are not standardized in terms of what is being done. So HIP and CUDA are evidently interoperable, but the question is, are they really? So what efforts are there to re-standardize this so that there is actually a single way of programming things in a sane way?
So I think multiple vendors have tried that game, right? They tried to CUDA, but then there's other ways to do GP. Now you have AMD coming to the market, which is a brand new player, and they decided to do their own thing. I think the standardization might not be something that's going to happen anytime soon, and I don't think that is really happening within the Exascale project either, simply because if you look at the Exascale project, even there, the software stacks are being kind of, the new types of hardware are being dropped on them too, and they get last minute. So literally the AMD was kind of a curve out of left field that that was not really, I think, anticipated. For example, we were anticipating Intel and NVIDIA as being the 2 kind of hardware platforms that are going to happen. So Intel, what they were planning is also rapidly changing. So they are coming up with their own sickle type stuff to get performance out of it. So you have Hipster, you have CUDA, you have sickle. So what turns out, the most thing that people are doing is actually finding ways to translate between those platforms right now, and not directly to optimize. One of the strategies that I think we need to take more, and we have taken that in a lot of ways, is that we are trying to abstract our coding away from the nitty-gritty of, do we need to do CUDA, Hipster, or sickle, and develop our tools at a higher level, and then have effectively relying on the software implementations that are coming out of the ECB project to get efficient implementations. If we as scientific developers have to go and fight this game with every different piece of hardware, which we have done for many, many years, NWChem has done that for 20 years, it is an enormous amount of effort. And the question is, can you afford the effort of both getting the performance out of the latest and greatest hardware while at the same time develop the new functionality that is needed for the next generation science that you want to approach. So it becomes a resource problem in the long term, right? And I think that's what you're maybe getting at too, is doing both is a hard problem. So we've been trying to develop abstractions that allow us to rapidly design codes for our domain, and then have a infrastructure that is as thin as possible, that allows us to go down to the hardware layers or the specific programming languages. So for example, our tensor algebra is not going to be a CUDA code or a hipster code or a SQL code. It is a general higher level language that can be translated easily to those. Is it going to be the optimal? Hey, if you can do things hand coded, it will always be more, well, it likely is more optimal than if you do it automatically generated. But our target is as much automated generated code as possible. As much automated code as possible, automatically generated code as possible, with a plug and play of different libraries that are needed.
Okay, thank you. So we can slowly shift to the discussion. And actually, I mean, we have some transition here, since there was a question raised by Matthew Smith in his talk that was about should we rewrite the DFT plane wave code? And I mean, here you can already give your own view on that, Bert, since you have a DFT plane wave part, if I understood correctly, in WChemX. So, I mean, and is C++ a part of the answer as well for the plane wave codes?
Well, I can tell you that we did rewrite the whole plane wave code from what was Fortran to C++. And again, it's a choice, right? It depends, I would say, the choice between rewriting or modifying depends a little bit on where you are with the software stack. Remember, NWChem was 20 years old. So there is a large amount of legacy. And
most of the plane wave codes are also that old. Huh? So
exactly, that's true. But I do have to say there is some more recent codes out there, right? So if you look at computational chemistry, there's also more recent codes out there that are C++ based. Sci4 is a good one. Hey, PySCF is completely Python, right? So people have taken longer, different approaches. But what's interesting with those codes generally is that they are not running large-scale parallel simulations. So we're trying to bring pieces together that are a little bit more challenging. It really depends again. So I think the plane wave codes could have gone either way. Although, because the data structures in general, plane wave codes are not as challenged. Well, I should not say that they are challenging anyway, but they have not changed as drastically when it comes to thinking about sparsification, right? So, and getting more sparse methods. A plane wave is what it is. Gaussian places that you can do a lot more crazy things. You can just go and drop stuff. If we would have gone with a plane wave code that was numerical grids, that's a different story, because there's a lot more you can do when it comes to the grid points and how you move data around. So for us, the plane wave code is because it's actually interestingly written, because it's Eric Balaska who wrote that C++ code. It's very much structured similar to what a classical plane wave code would have looked like, just in C++. So he's not taking advantage of some of the auto code generation that we do actually in the Gaussian part of the NWChemX code.
And if I may extend the question to Erwin, in the sense that, I mean, if we go beyond the plane wave code and then we see all the DFT code, is the fact that they are written in Fortran, is it some kind of a problem in the long run? Is it difficult to find the developers for Fortran, or, you know, rewriting that in a different language like C++ might be one way to go?
I think it's definitely a problem on two sides. So you said finding good Fortran developers is getting increasingly challenging, right? People are not taught this anymore at university, and they probably learn them during their PhD or even only at the postdoc level. And then, of course, the level of knowledge kind of is limited, right? And I think Matthew has shown this pretty well, that the modern developments with GPUs, what NVIDIA is doing, but also what Intel is doing, they are not focusing on Fortran anymore, right? When I talk to Intel, and as Bert said, they're going SQL, yeah, perfect, wonderful. And I asked them, so what do I do with Fortran codes? They said, oh yeah, Fortran codes. Oh, well, I use OpenMP, that's fine, yeah, it will work. Yes, it will work, but will it be performant? Yeah, that's remains to be seen. So I've also examples back from KTH where people worked, actually, Bert, you might know the code, it's part of the ECP project, the NEC 5000 CFD code. And well, I think there's still discussions going on, but at the end, the KTH team decided if we really want to go to GPUs, we have to do this in C++, right? There's no way we do this in Fortran. So they are currently in a kind of hybrid mode where parts stay in Fortran, parts go in C++, and whether this eventually will end in a complete rewrite remains to be seen. But I think particularly using GPUs and other modern things, there will be more hardware coming, and the memory layout and all that. I think it will be very difficult if you just stick to Fortran.
Matthew, since you raised the question in your talk, maybe you can give your view on the topic. And anyone can chime in and give their opinion as well.
Yeah, sure. Well, it's interesting to hear people talk about it at more of a macro level. I mean, I'm interested to know in rewriting the plane wave code. I mean, how much work is involved in that on the scale that you're talking about? Are you essentially saying, right, well, let's just rework this from scratch? Is that what it takes?
Well, that's the impression that was given by Bert in his talk. That's what they did for NWChem-X.
Yeah, so that one was completely rewritten in C++, yes.
Yeah.
But that was actually, so it's interestingly, so the plane wave code is a single person effort within in NWChem-X. So it wasn't that big of a effort to do. But again, it's just a straight rewrite. I think one of the things that one really should think about is, what is the goal of the plane wave code? Is it the goal to get performance out of the next generation pieces of hardware, or they just want to run science simulations? If it's the first one of the things that you see a lot of in the ECP project is code starting to think about what I mentioned already before, finding a level of abstraction away from the specific CUDA, NVIDIA, CUDA, SQL, hipster type languages. So find a way to have a higher abstraction, because that's where the scientific development needs to happen. And then rely, and it will never be perfect, but rely on those lower level translations to the specific programming languages, because that allows your code to be as agnostic to the hardware as possible. Yes, you will not get the maximum performance out of it, but you need to spend an awful lot of time getting performance out of hardware. And the question is that really the goal of the code that you're developing? In a lot of ways, your goal is to deliver science, do science with your code using the latest hardware. So my view has always been is you probably need to try spend as little as possible on the hardware specific stuff, and as much on providing a tool set and a infrastructure that allows developers to focus on the science. And NWChem initially tried to do that with the global arrays framework effectively, right? We don't have to worry about parallelism to some extent. We just use the global array framework. but this was within the Fortran era, effectively, and in a very abstract, object-oriented way of thinking. It worked reasonably well, but heterogeneity and concurrency just have defeated us in the original code by now. So that's why we chose to do the rewrite, because of the scales of the problems that we want to run. I think if we go back, if we take a WChemX when it comes out and you run it on a small platform, it's not all these challenges with hipster, CUDA, and so on are not going to be the challenge. It will perform on small platforms simply because it's not going to be that different in a hardware sense. So honestly, yeah, you need to think about, if you want to rewrite something that allows you to abstract away from the hardware specific pieces.
Matthias?
Yeah. So a question to all of you guys. I mean, basically, long ago when I did my PhD, Fortran was already dead. But I mean, it is still there. And the reason is that the compilers were really always a little bit better than the other ones. Actually, in some intermediate time, even much better than other ones. So my question is really, if you nowadays would do these things in Python plus C++, so really in this combination, which fits together well, are there really compilers which are comparable to what we are used to in Fortran?
Well, the problem is that not all platforms even have compilers, right? For Fortran. That's the real problem, is that a lot of vendors don't care.
Yeah.
But I think one of the issues is not so much the compiler, but it's the programming style. You can program C++ very efficiently, and you can have pointer redirection all over the place, and you're just chasing pointers, and then the compiler can't do anything. So I think it's a lot also on the programmer to make the programmer program in an efficient way, so the compiler can generate efficient code. Fortran didn't allow you to write in an inefficient way, so that was the good thing about Fortran, or is the good thing about Fortran still.
But shouldn't a good compiler solve a lot of these software hardware problems? I mean, can't you really shift some of these problems to the compiler level?
Well, that gets back to, if we abstract it to a level that the compiler can do the rest, yes. And that's what you do see. So there's in the software infrastructure of ECP, they are developing kind of those intermediate levels that provide us the tools to go straight to the low level, and then the compilers know what to do. It's that kind of the C++. Yes, we can go crazy in C++, so you have to not do stupid things. Don't think like a human, think like a computer when you're programming, right? But in the long run, there needs to be a level where we program and a compiler takes over. And if we dive too low, then it takes us more effort. If we go too high, it takes the compiler too much effort. So there's always we need to find that happy balance, and I don't think anybody has really found that kind of middle ground where we can get the maximum performance out of a compiler. And that's why you see all these different programming languages show up too, because effectively what they do is they kind of constrain you back. They take C++ and constrain you back to what they want you to do so that the compiler can do the best thing they can do.
Claudia? We'll see more of the...
No,
sorry.
go ahead.
Claudia, go ahead.
Actually, related to this, some people tell me that Fortran 2018 is another big step forward, and that's why I'm a bit surprised that that Fortran is again predicted to be dead.
I'm not saying, I have not said it's dead, right? But it depends on where you're going, and the vendor support is diminishing. That's definitely what you see. And yes, the standardizations efforts, they are going on, and Fortran 2018 is probably a step forward. I haven't followed it closely, but will the vendors pick up on it? Will there be efficient implementation? That remains to be seen.
Yeah. Yeah.
I hate to say it, but at the higher level, the Fortran code, that the higher numbers in the Fortran standard, the closer they come to C++.
That's also true.
Phil?
Thanks. Yeah, just on that note, really. I mean, 10 years ago, we were asking Intel about compilers, and they told us that the C++ team, depending on how you counted it, was 28 to 50 people, and the Fortran team was 2. And Fortran beat C++ hands down then. But 10 years of that kind of effort going into a compiler, and they're surprisingly close. So to go to your point, Matthias, you would be surprised what a C++ compiler could do with code that you would look at, humanly and go, well, this cannot perform well. But the compilers can, especially with templates and some of the modern C++ abstractions. But they're coming into Fortran, and there's also FIP, the Fortran preprocessor, which can do some templating things in Fortran and other nice things. But is there a Fortran 2008 compiler, fully compliant? I'm not sure there is.
Actually, I also asked about
this
combination, right? I also asked about, say, the combination of Python and C++, which people usually like very much. Yep. But would that also be fully supported by modern compilers?
I think that would. I mean, the route we're going is Python with Fortran. So we're taking that route. We're sticking with Fortran kernels and then letting scientists stitch that together in Python. And now Fortran is interoperable with C and C++. That means that actually they can interoperate at a low level or a high level. We can interface with system level kernels within Fortran now without having to jump through vendor specific hoops. So I think if your design is right, you can do good things in most languages. Or to repeat an old saying, a good programmer can write Fortran in any language.
I second that.
Yeah.
If I could make just one small comment. So there was, I can't remember who said this, but someone was saying that the focus of the scientist is on running software to get science. And I absolutely agree with that. And you might ask questions like, is it worth 12 months of a postdoc or a research software engineer in your group to get a 5% performance improvement or something? But if you move to someone else, like someone running a tier 0 or tier 1 HPC facility who might have 40% of their cycles in VASP or Abinit or Quantum Espresso, if you start saying, would you like an extra 5% of your facility, that's a much more attractive thing to them. So if you can have 5% of your machine effectively for, say, 12 or 24 months of person effort, that's very attractive from a supercomputing perspective.
Absolutely, Phil. I think that's a key point. At the end, we're talking money, right? And 5% of an exascale machine costs a hell lot of money. But what you are pointing at, I think, is really something the community needs to think about. And this is getting more professional in software development. Of course, if you have a material science postdoc, that person is supposed to do material science and not optimize the code 90 or 95% of his or her time, right? So I think we need to get there, that we have more of these professional academic software engineers that work alongside the scientists, but take away the heavy lifting from the scientists so they can actually do the science.
Here.
Matthias?
Yeah, no, I think actually these developments require probably really the combination of good scientists. I mean, good scientists always had to write these codes because you need some concepts which has to come from the science, but having more support really from software engineers is exactly what we need. And this is actually also how Erwin's team is operating, which is actually great. I'm still wondering, actually, I mean, as we said, mean, there is, say, which when I was younger was Amdahl's law, and somewhat we are fighting with this when we say about workstations, workflows. Does it really make sense to have an exascale computer, or is it better to have 1,000 petascale computers? So what is cheaper? I think for the scientists, 1,000 petascale computers would be more efficient.
Matthew, I don't know if you want to answer this question or if someone else wants to answer this question.
I think it was more of related to a question that I wanted to ask rather than answer. In fact, it relates to a question I wanted to ask. But in particular, he talked about designing the code to be a thin layer for the to be optimal for whatever the hardware is that you happen to have at hand. Because what we should be interested in is the time to science and just getting the science done, and fair enough. But I wonder how, if you pursue that as a policy, do you not run the danger of ending up with software that really isn't using the hardware to the extent that the hardware is capable of, to the point where actually you are just wasting money, and you say, well, why do we have all this hardware if we're not actually using it? Is it just a case of, well, that's what's there and it's being used in other fields, therefore that's what we end up using, and therefore we don't really care? Is that maintainable? If that is the end point of that kind of approach, is that maintainable? I'm interested to hear what you think.
Well, it has been, so NWChem has been maintained for 20 years, but we had a lucky source of continuous funding, right? We were part of a construction project at that point in time called the Environmental Molecular Sciences Laboratory, and we were kind of an instrument. And so we had continuous funding. That allowed us to actually develop the code and maintain and get it ready for the next generation platform. That kind of support is going away. It just doesn't exist anymore. So a lot of our software development efforts are going to be very project-based. So it's going to be science-driven. So these ECP projects, these kind of construction projects, are a unique opportunity, and isn't a unique opportunity for us as a entity, as a group, to really kind of build that next generation construction project code and hope that we can then use continuous project funding to advance the capabilities. But the problem is we'll never have, again, really a constant set of funding to continuously improve the code with the next generation hardware platforms. So that's why we chose to get an infrastructure that is, and build an infrastructure such that we can get the performance to a level that is, I would say, good enough. Sure, we can go still to a HPC supercomputing center and say, hey, if you put some people on there to get more performance out of this part, you might get more bang for your buck. But that is going to be harder and harder for the scientific development teams. And so there is also a very conscious reason why we chose to build, yes, we're going to build an exascale code, but we are very conscious of how much we can get out of a single node, how we can get out of a single GPU. Because as Matthias was saying, is the question, is an exascale computer going to be the best thing since sliced bread, or is it 1,000 petascale computers, or even 100 petaflop computers better? We have, NWChem has had a user base that goes from a workstation to exascale effectively. So that's always a challenge, has always been a challenge. We have marketed us as scalable code. That means you have a user base that is broader. If you don't have that marketing, then it's a little easier, I think. But reality is there will be exascale computers, but there will be few of those. we need to be able to run at the petascale. And what's interesting is, even though we're developing our exascale code, reduced scaling methods, we already know that it's going to perform at petascale performance. So this provides us some comfort that there is a way broader user base for all the smaller systems that are going to be available in the long run. And yes, there will be only a few exascale machines. Simply the power, the cost, it's just not sustainable. So we will be ready. We are ready for petascale. We've been with NWChem already at the petascale, but we're definitely getting more bang for our buck with NWChem when we have petaflop machines.
So, Bert, I second most what you said, right? But say the cost, whether you have one exaflop system or you have your 1,000 petaflops, your energy bill will be the same. You just don't see it, right? Because you distribute it over 1,000 sites.
Sure, fair.
Yeah.
Yeah.
So, but at the end, in the global view, it's the same. But I agree with you, we'll only see a few exascale systems. And I think for me, the reason is that typically you try to leverage economies of scale, right? And you build larger systems, typically it's more efficient. You need fewer people, you probably get a better hardware deal and so forth. With Exascale, we are getting into dimensions where I'm not quite sure these economies of scale still hold. Yeah, you need to invest so much to get the electricity there, to get the cooling there. We're getting into dimensions that are really enormous. Yeah, and that's why I'm not certain we can make this economy of scale argument. We can make it for the tens of petaflops, maybe for 100 petaflops, right? But for the exascale, I'm not quite sure. And I just seen it in other examples where people were thinking of how they get their computing hardware together and build a new large system, right? And just what they were thinking of, they're getting, yeah, well, we would need 20 megawatt. How many sites in the world you find that will say, oh yeah, I have 20 megawatts available, just come here, I run the system for you. It simply doesn't exist, right? And so this will be one of the big problems. But the other aspect, of course, is as you said, there are problems that require the exascale, right? And then, of course, it's a political question whether you want to give them their tool or not. But there is also and even more problems that require tens of petaflops or maybe hundreds of petaflops. And as we all know, if you have such problems running on a machine that is 10 to 100 times larger than your problem, your throughput is much increased, right? So that's another challenge.
I think the power story is not, I would disagree a little bit on the power story. So one of the interesting things with the Exascale was that when the US chose to build Exascale machines, they told the vendors they needed to have a power envelope of so much megawatts. What's the nice part of all of this is that all these vendors, they got money from the government to do that too, but still, all these vendors are now developing energy efficient processes. Mm-hmm. What's interesting, so it does have an advantage on the power side because these technologies will flow down to the smaller systems. So a petaflop machine or a 10 petaflop machine right now, its power consumption will be going down when they build the next. If a supercomputer center has a 10 petaflop machine and they buy a new 10 petaflop machine, their power envelope might be whatever, 50%, 60%.
Absolutely.
So it turned out that, yes, fair, if you have 1,000 petaflop machines versus 1 exaflop, that power, well, the power might actually be a little less on the exascale because cooling might be more efficient. But the advantage of these kind of efforts, these races to the exascale, have been that the power envelope across the supercomputing world has drastically reduced. So it was good.
I think we are in violent agreement here. So
yes, exactly, I think we are.
Okay, Matthew, you still have your hand raised. I don't know if that's remaining from before or if you want to ask.
So yeah, sorry. Let me.
Okay. So I think this is a nice point to stop. It was a very lively discussion. I'm very happy for that. So I would like to thank you three for your very nice talks and for this very nice discussion. I'd like to thank everyone for participating to this workshop. It was my first hybrid workshop, and I really enjoyed that. We had this conference dinner, which was something that we hadn't had for a long time, so it was great. And so I hope that you all enjoyed this workshop, and so I thank you very much, and maybe we'll see soon for another live experience. Thank you very much.
Let me just add a little thing. I mean, you know, there were several organizers of this workshop, but there's one person, and you know who that is, who really did most of the work. And I think the workshop was really very good. I mean, I've seen few workshops where we had so many high quality speakers. So, and for the work Gianmarco has done and put into this, I think we all thank him very much. Thanks, Gianmarco.
Thank you all. Thank you.
And goodbye to all of you.
Bye-bye.
Goodbye. Thank you.